Yeah.
Where are you?
Still in Cambridge.
Are you in? Yeah, I see. Okay.
How about you?
Well, I'm in Beijing,
Nice.
China.
Oh, man. All right, let's go. Okay,
great. So welcome to everybody who is coming to this annual conference on big data. First of all, I'm Yao, who is the director of CMSA. CMSA has been running for about 8 years. And from the very first year, we pay attention to big data. So Scott has been with us all these years, and each year he has been helping the conference. And later, Sergey joined in and has been great help in all these last few years. And big data has been extremely interesting and important. And CMSA is interesting to see how mathematics can be applied to all kinds of science, including social science and economics. So big data is naturally a very important subject for us. And we encourage our members to look into it from many different points of view. So we have collaboration with people in business school, in economics, in all kinds of different areas. And big data has been also an important subject in Harvard, and we are collaborating with all different departments in Harvard, and we are proud that we are doing it. And now we see that large number of people coming to this conference. Well, we used to be meeting physically, and very nice to see each other, exchange ideas. Because of virus, we have been not been able to do it in that way. It has been online, but still, we still draw a lot of attention. So I think that's great. It shows the importance of the subject, and there are many interesting open problems to be solved. And I think that's exciting for mathematicians, collaborating with people in different subjects. So I'm glad that you are here, and I hope by next year, the same time, we have the same conference, then we can meet each other physically. And I hope great success for this conference. Thanks to Scott and Sergey. Thank you.
Thank you, Professor Yao, for the introductory talk. Let me introduce our first speaker, Andrew Bloomberg. So Andrew Bloomberg is now based at Columbia University, where he is now the Herbert and Florence Irving Professor of Cancer Data Research, as well as a Professor of Mathematics and Computer Science. Yes, you've heard it correctly. Andrew has obtained his doctorate in mathematics, but currently he works in a very broad range of fields, combining research in mathematics, computer science, and biology. From Andrew's vantage point, this is a very natural development, and in his just published book, he declares that biology has entered the age of big data. In light of all this, I am sure today Andrew will bring a new perspective on the problems and questions we are all excited about. Andrew, the floor is yours.
Thank you. Thank you for the introduction, and thanks to everyone for inviting me. I'm honored to speak. Let me share my screen so you can see my notes. And then, okay, here we go. Okay, so the subject for today's talk, the broad thematic area, is geometric data analysis. And specifically, I want to talk about robustness and stability phenomena in multi-parameter persistent homology. But to give you context for what this is about, the idea is that data has shape, and we can get at that shape using various kinds of tools for data analysis, some more familiar and some, I think, somewhat less familiar. And this talk is about how to provide mathematical foundations so that it's sensible to use some of these tools for robust scientific inference. So let me get started by reviewing a little bit about what persistent homology, which is sort of at the core of topological data analysis, what that is. So persistent homology, this is a higher dimensional analog of hierarchical clustering. So our basic assumption that we'll make throughout this talk is that the data we get is presented to us as a finite metric space. Often we'll think of this as being sampled from some underlying ground truth infinite metric space. And a good example to keep in mind is, for instance, that X is a subset of M, where M is a compact Riemannian manifold. And so we're sampling according to the volume measure, and we have some finite sample from M. This, I should say, that this is both a very good motivating example and sometimes somewhat misleading, because in many cases, especially in examples that come from biology, it's often the case that the metric that we have doesn't behave very much like a Riemannian metric. And for instance, if you use the Hamming metric or some sort of edit distance on strings, the metric might have a minimum distance and might have sort of a very different character. But if you're, depending on where you come from, this is a familiar model to think about. Okay, so let me start by reminding you about hierarchical single linkage clustering. So hierarchical single linkage clustering gives us a multi-scale shape descriptor. And so how do we do this, and what do I mean? So first, let's fix an epsilon greater than 0. This is a real number, and this is our scale parameter. And given our data X and our parameter epsilon, we form a graph, G epsilon. The vertices of this graph are the points of X, and the edges connect points Xi and Xj precisely when the distance between Xi and Xj is less than epsilon. So, if your data looks like this, and epsilon is maybe a scale, something like this, then, we'd connect these points, and maybe these points, and this point, and maybe we wouldn't connect those points. The clusters, the clusters one gets in single linkage clustering are precisely the path components are defined to be the path components of this graph. So here that would be this, and this, and this, and this. And another way of saying that is that Xi and Xj are in the same cluster, the same path component, if they're connected by a path of points through this graph G epsilon, such that the distance between adjacent points is less than epsilon. Now, the key observation that leads to hierarchical clustering. So here, let me step back. Here we've fixed a scale, epsilon. And epsilon you should think of as the feature scale. This is telling you at what scale you expect important geometric features of the data to arise. And of course, in principle, this is unknowable. I mean, if you know your data set, you have some idea, no doubt, of what the right feature scale is, but there's a wide range. And moreover, choosing a single feature scale is often the wrong thing to do, because even if you do know and have prior information about epsilon, in many realistic data sets, there are different feature scales at which different kinds of structures emerge. And so fixing one of them isn't the right thing to do. So a key observation about this graph we've formed is that if epsilon is less than epsilon prime, G epsilon is contained in G epsilon prime. And this is because if an edge is in G epsilon, if Xi and Xj, the distance between them is less than epsilon. But of course, if that's true, and that distance is also less than epsilon prime. And so G epsilon prime has all the edges of G epsilon, possibly plus others. And another way of saying this is that if we look at R, I guess, greater than or equal to 0 as a poset under the usual order, then what we have is that we have a functor from R greater than or equal to 0 to graphs. And I'm not going to spend a great deal of time on the categorical perspective on this, in a precise way, but it's lying underneath all of this is that these processes are functorial. And I guess we'll see that in a little bit more in a little bit. So the impact for the clusters is that the clusters in G epsilon prime are formed by merging together some of the clusters in G epsilon, because these new edges might connect clusters. If we had, here are our points in G epsilon, maybe I should connect those. Then eventually, when epsilon is large enough, we'll have an edge that connects across and get a new cluster that merges those clusters. And so we can represent this process, or the output of this process, in terms of a graph that looks like a tree, and it's typically called a dendrogram. So the dendrogram maybe looks something like this. And the way to look at this is that on the x-axis, we have epsilon, that's the scale parameter, and each vertical slice of this graph tells you the cluster structure at feature scale epsilon. And as you move in the graph, it tells you how the clusters merge as epsilon increases, or how they split apart as epsilon decreases. And so this is a multi-scale summary of shape information from the data. But now what we want is, this is a very crude kind of geometric invariant. So on the one hand, clustering is wildly successful. I think I can't maybe estimate the percentage, but some very large number of papers involving scientific analysis in biology in particular involve some kind of dimensionality reduction and some kind of clustering. This is a standard analytic pipeline. At the same time, clusters are crude. If you think about what are you doing? You're finding clumps. And we know, in our life that there's much more to shape than just component information. So we're going to generalize this to higher dimensions. And instead of a graph, we're going to form a simplicial complex. So what is a simplicial complex? So a simplicial complex is a combinatorial. So what is this? This is a combinatorial model of a space. And what does combinatorial mean here? Well, we're going to describe it in terms of pieces that start out by looking like a graph. We have the data of a bunch of points, and those are called the vertices, or the zero simplices. And those are the points of our data of X. And next, we add some edges connecting the points. And those are called our one simplices. But now we keep going. If we have from just a single point, you have a vertex, you have a point. From 2 points, you could have an edge. So you could have a one-dimensional object. You could have a point, you could have an edge. If we have 3 points, we could have a triangle or a simplex. And so here, maybe we connect these ones, and now we have this simplex. And maybe we connect these ones, and we have this simplex. And from 4 points, you might be able to have a pyramid. And the idea, a two simplex, and the idea is that this is a model of spaces that we can make by gluing together standard geometric objects that look like triangles and higher dimensional triangles. These are, another way of looking at this is that these are the convex hull of the unit vectors in Rn. So some, xi greater than or equal to 0, and you choose a vector such that they sum to 1. So the complex that we're going to assign to our data, in analogy with single linkage clustering, is that we're going to add where the zero simplices will be the points. Oops. Let's do this. So the zero simplices will be the points. The one simplices will be just like with the graph we made before, so that we add an edge if points are within epsilon of one another. But now we add a triangle for a triple of points if pairwise each pair is within epsilon. And so if you think about this, this is determined by what happens this is determined by what happens in dimension 1. And this gives us some kind of, and so if you're familiar with this, that's great. If you're not, the way to think of this and the picture to have in your head is that from a discrete set of points, we've now produced a continuous geometric object by using those points to produce instructions for gluing together triangles and pyramids and higher dimensional tetrahedral solids. And so now, instead of the path components, so before to get the clusters, we got the path components. Instead of the path components, we take the homology of this thing. And the homology is a collection of functors indexed by an integer parameter k. And the kth homology is something like a count of, roughly speaking, is a count of the k-dimensional holes in X. So for instance, if we have some points, then then H0 is a count of the points. That's just the components, 1, 2, 3, 4, 5, 6, 7, 8. Oops. H0, really it's a vector space maybe of dimension 8. And if we connect these by one simplices like this, then the idea is that H1 is supposed to see the loop that goes around this hole. And so H1 might be a one-dimensional vector space. And if you had higher dimensional surfaces and higher dimensional holes, you would get things in H2 and so on. So the index K is the dimension of the geometric structure that we're finding. Now, the interesting part, again, the first interesting thing to observe is that just as our graphs were nested, as our scale parameter changed, the same thing happens for our simplicial complexes, and basically for the same reason, namely that when you form VR epsilon prime, so VR stands for I should write this, is the Vietoris-Rips complex. This is a particular way of making a complex. There are others, but we'll focus on this one for sake of concreteness. And this has our metric space X as a parameter, and it has the scale parameter. And now, as we vary the scale parameter, VR epsilon prime is formed from VR epsilon by adding edges, adding triangles, adding simplices. So VR epsilon is a subcomplex, a subset that sits inside of VR epsilon prime if epsilon is less than epsilon prime. And so once again, this is a functor from r greater or equal to 0 to the category of simplicial complexes. Now, given this functor of complexes, we can apply homology, and we get a map of vector spaces, or really a system of vector spaces. And the key insight of persistent homology, which is, they're due to many people, but maybe I would single out Robbins and Edelsbrunner, Letcher, and Zamarodian and Carlson, is that if you think about this system, you can summarize it in an interesting way. And the idea is that if you have an element alpha inside one of the homology groups, and remember that's a representative of some kind of hole or some shape feature, then there exists sort of a maximal epsilon such that eventually I think I wrote maximal and minimal wrong. There exists a minimal epsilon such that something hits alpha, and a maximal epsilon or a minimal epsilon such that alpha is mapped to 0. I didn't write this very well, but the idea is that at some point alpha appears and at some point alpha disappears. And the picture the sort of characteristic picture for this is something like, this. And what's the idea? Well, when epsilon is small, when epsilon is 0, you just have points. When epsilon gets a little bit bigger, you start connecting things. And eventually you connect and you have this central circle. that gives us in H1, that gives us a circle. And then after a while, epsilon gets even bigger and you crosscut and this thing becomes a disk and the hole closes up. And so the way you summarize this information is by sort of a generalization of the dendrogram, which is called a barcode or persistence diagram. And what this looks like is, well, a picture with a bunch of bars. And each bar is a feature, is a hole or a shape feature. And the length of the bar tells you when did it appear and when did it end. So down below, this is epsilon, on the x-axis is the feature scale, and the y-axis is not meaningful. It's just a way of ordering the features, and that's done arbitrarily, essentially. Now, when you do this, the key observation that one makes from this move is that something interesting happens that's not true in a good way about homology, which is that the set of these barcodes itself forms a metric space. And the metric on them is kind of a matching distance. You look for the best matching between two barcodes where, if we're matching this barcode and this barcode, then the idea is something like you match this to this, and you match this to this, and the penalty, the distance, is the discrepancy between matched bars. So you search for the best such match. So that's something that's algorithmically computable. It turns out that satisfies the triangle inequality and gives you an honest metric. And this means we can talk about when data sets are close in terms of their shape descriptors. I will also note that from a formal perspective, there's a way of thinking about this in terms of being closely related to the idea of an approximate homotopy equivalence. But I won't say so much more about that, at least at this point in the talk. One thing to say is that you can describe this metric algebraically. This is in terms of the barcodes. You can describe this algebraically in terms of the systems of vector spaces that you got directly by what's called homotopy interleaving. And the idea here is that two sequences, so if we have this filtered sequence of vector spaces, and we have another one, what it means for them to be close in the barcode metric is essentially that we have maps that go back and forth such that this composite is the identity, and the direction that the amount that you have to shift is effectively the distance between them. And this is called an interleaving distance. And it looks like a system of maps from x alpha to y alpha plus delta and y alpha to x alpha plus delta that form sort of a ladder diagram that commute. So the main theorem in some sense, or maybe not main, but the most important theorem in the subject is what's called the Stability Theorem, which in its original form is due to Cohen, Steiner, Edelsbrunner, and Harrer. And morally speaking, what this theorem says is that small perturbations in the input lead to small perturbations in the output. And let me give you the formal statement, and then I'll say more about it. So what it says is that the bottleneck distance between the persistent homology of x and the persistent homology of y, so here we have two data sets, x dx and y dy. These are finite metric spaces presenting our data. And if we take the persistent homology of each of them at dimension k, and we get these, we get from each of these, we get some kind of barcode. The distance between those barcodes is bounded by the Gromov, what's called the Gromov-Hausdorff distance between x and y. And the way to think about the Gromov-Hausdorff distance is something like you try to do arbitrary rigid transformations and more to get these two sets spaces to be as close as possible together, these metric spaces as close as possible together, and then you measure some kind of discrepancy. So more precisely, one way of defining it is that you take the min, or the inf really, over all embeddings of x and y into some bigger space. And this is how you could rotate them any way you want, and you put them in Z. And now inside there, we look at the penalty of finding the minimum epsilon such that the image of x is contained in the epsilon fattening of y, and the image of y is contained in the epsilon fattening of x, where by this epsilon fattening, I mean you take all the points that are within epsilon of your set. So, if this is our X, then the epsilon fattening is, you fuzz this out and you get this stuff too. Or if epsilon is big, you get more and more. And so this is a metric on the set of metric spaces. So we have a metric on metric spaces, we have a metric on these shape descriptors, and this theorem says that the process of computing the shape descriptor is continuous and satisfies this a Lipschitz bound. And so this result, why is this important? This result controls the behavior of these invariants. Oops, let's get back to the highlighter. This result controls the behavior of these invariants when there's noise that's concentrated around the data set. Two things are very close in Gromov-Hausdorff distance, essentially if all of the points are pretty close together. Because if you think about this, if you take 1 or 2 points and you move them far away, that will make this sort of discrepancy very big, because there's no way to get those to be close to the core of things. But it's good for the noise model where you have your data and you've added Gaussian noise concentrated on the manifold. It is not good for arbitrary outlying points, and in fact essentially says nothing when you add even a very small number of outliers. And so to be precise, what you would say is that this persistent homology, this is not a robust invariant. I think I learned this term from Shmuel Weinberger, but this is sensitive to sort of what you might call handle bodies at infinity, but meaning you could put very small, arbitrarily complicated geometric objects far away from the bulk of your data and change these invariants. So this is a problem for practical application, because of course, in your real data, you might well have noise that is not concentrated, or depending on the generation process, you might well have noise that is not concentrated around the signal. And so you need to do something about that if you're going to use this stuff. So, it brings up this question: how do we handle outliers? So a standard approach, which is a standard approach that one does in any kind of data analysis, is effectively to smooth the data by doing some kind of density filtering. And there's been work on this. There's been a bunch of work on this. Two things I want to highlight. One of them is something called Distance to a Measure by Chazal, Cohen, Steiner, and Marigot. I did some work with Ida Margal, Mike Mandel, and Matt Pancia. And both of them, the idea is somehow that you think about controlling for density. The idea being that you're going to distinguish outliers as always by assuming that they're lower density than the bulk of the signal, or that they're separated from the signal somehow. But that work that I'm referring to handles this essentially by fixing a density parameter or some sort of threshold or cutoff typically, or a sampling parameter, something, a width, something that controls how we think about the density. And a lot of the power of this approach of persistent homology to begin with is this idea that we don't know what the right feature scale is, and so we're going to take all of them. And here, it's unattractive to have to introduce density or width parameters. And so what I want to talk about now is work designed to think about how could you incorporate density directly into the construction of persistent homology. And this leads to this idea of multi-parameter persistent homology. And the idea is just that in addition to a scale filtration, you have an additional parameter filtering the data according to, let's say, according to density, or maybe something else that also is allowed to vary. So, and I should say that, this is work of Carlson and more, lots of people, but maybe originally Carlson, Morozov, and De Silva. And let me give you some examples of how, and this is a very natural thing to consider, because at the beginning, I said our model of data is a finite metric space. But really, your data might well be an image, which has both spatial coordinates and brightness. So you've taken a picture of tissue and you've stained the tissue depending on some relevant biological quantity. And now you have a grid where at each spatial point, you have some kind of staining, as well as maybe information about the presence or absence of tissue there, or cell, or whatever, whatever it is. That immediately gives you two filtration coordinates of interest. Another one that's pretty standard is density. And this is in some sense invented to imagine that you have a local density estimator. Let's say, you get a parameter from, the distance to the kth nearest neighbor, fix k. And this is some local measure of density. And now you'd like to filter by that. And so the kind of thing you might do is, imagine this, coming back to this brightness example, is you might think about analogs of the simplicial complex we built, where now there are two parameters. There's a parameter epsilon, which is the scale, but there's a parameter alpha, which is the density. And maybe you say you only take points that are at least as bright as alpha. And then you, having restricted to those points, you then construct this complex as usual using the scale parameter. And so what this leads to is a multi-indexed collection of simplicial complexes where you have two parameters, and you get maps between them if from xab to xcd, if AB is less than CD in some in an ordering induced by the orders on each scale parameter separately. And so what this gives you now is, whereas before we sort of had a line of stuff, now we have a grid of invariants. And this is the two-dimensional example. I should say that, of course, you could do this in 3 or 4 arbitrary dimensions. And you can apply the homology to this, and you get now a grid of vector spaces. But now there's an issue, which is that there's no invariant. We got a lot of mileage out of the fact that there was this summary of these chains of homology in the case of one-dimensional, one-parameter persistence given by these barcodes. But here, as a matter of representation theory, it turns out, or sort of structure theorem for modules, it turns out that there is no simple invariant that classifies these things like that. And so as a sort of highlight of an interesting open problem, there's been lots of work on understanding what we do have, but I think there's plenty to be done in the search for simpler descriptors for these kinds of things. Notwithstanding, so what kinds of things might you do? So there's lots of different summaries. So one thing you could try is, I could look at a line like this. That's not such a good line. Let's make a narrower line. There we go. And what is this line doing? This line is a slice through the parameters that turns these two parameters into a single parameter, right? As you walk along, the parameter is walking along this line, and that goes, over and up. So it goes from xab, let's say, to xa plus epsilon and b plus delta. And now this is a single dimensional filtration. And for this line L, you can compute a barcode, and maybe you keep all of those as your line rotates around. This is sometimes called the fibered barcode, but it's a parameterized family of barcodes, and that under reasonable hypotheses, these vary smoothly or relatively smoothly as you move. But there are lots of other things you could do. This is just sort of a representative example. Now, a key fact, though, is that the output of this two-dimensional process remains a metric space. And there are no barcodes, so there's not a barcode distance, or this sort of matching distance, but there is a version of what I call this interleaving distance. So remember, that was this ladder connecting two filtrations, and I'm not going to draw this, but if you think about some sort of multi-dimensional honeycomb or something, there's a way of thinking about interleaving where sort of you have one grid of vector spaces and another grid, you can control how much you have to shift them so that there are compatible maps between them. And this is called the sort of the homotopy interleaving distance. And this is the appropriate generalization to this setting of the metric we had before. So now we can think about using this. So I want to now talk about how to use this framework to incorporate in a parameter-free way a scaling by density as well as by feature scale in order to get robustness results. So our setup for this, we want to have probabilistic result. And so we're going to consider a metric measure space. So our model now is that our data, our underlying ground truth is a metric measure space. So that's a finite metric space, or maybe an infinite metric space now, x dx, equipped with a measure. So a way of integrating defined area. And I'm going to assume that these are probability measures so that the measure of the whole thing is 1. And that's a model for where our input is coming from. Maybe we have access to this thing. Maybe what we really have access to is a finite sample from it. And this is just a way of formalizing our sampling assumptions. And now I'm going to make some definitions. So there are a couple of, and these are just some representative examples. There are others, but for sake of discussion, I'm going to give two sorts, a bifiltration on X, where there are two scale parameters, epsilon and r. And at epsilon r, we take the points of X such that if you take the r ball, the ball of radius r around that point, and you ask for its measure, that measure is at least epsilon. And this is a measure of density, right? You're saying if you take a ball around that point, that it's bigger than epsilon in terms of, and that's, you know, if you're discrete, that's just how many points are in it. It's a count. If you're continuous, it's a continuous measure of density. So this is kind of a continuous thing. And if you want a more combinatorial one, then we could think about this thing called, which you think of as what we might call the degree RIPS. And here, what we're doing is we are taking the subcomplex of VRR, and we are restricting to the part of where the vertices have degree in that underlying graph at least k-1. So again, the degree of the vertex is some measure of its density or centrality. And so this gives us a two-dimensional filtration where you can change the scale parameter of the simplicial that produces a simplicial complex, or you can change the set of vertices by changing degree. And now in this context, we can prove stability results. And these stability results are expressed in terms of probabilistic metrics, namely the Proorov or the Wasserstein metric, and or their infinite versions, the Gromov-Proorov or Gromov-Wasserstein metrics. So what are these? These are metrics on distributions. So if you have, the idea is that if you have a metric space, and I have two distributions, mu and omega, let's say, these things give a distance between mu and omega, and the Wasserstein metric is an earth mover distance, or it's an optimal transport distance. So what it controls is how much, sort of the cost of a minimal plan for moving mass around to turn one distribution into the other. The Proorov distance is is another way of getting at sort of how to compare these things in terms of discrepancy between the size of balls. And so from these, we can produce, of course, also this sort of Gromovized version where we look at embedding of X and Y into a reference space Z, and then look at the Proorov distance between the push forwards of our measures on X and our measures on Y. And these metrize weak convergence, which means that convergence in these metrics means that you have weak convergence probability measures, so all the expectations of all random variables converge. Okay, so this is a particular kind of, and I guess I should say that in the background, I am assuming that my metric measure spaces are Polish spaces, so they're separable and and have some local niceness properties. So now the theorem here, and so which I proved in joint work with Mike Lesnick, is that if you think about this density, this intrinsic density bifiltration, once again, you get a stability result that says that the interleaving distance between these bifiltrations is bounded by the Proorov distance on the measures on X and Y. And this is a robustness result. So I want you to think of this as a robustness result, because the Proorov distance and the Gromov and the Wasserstein and the Gromov Proorov and Wasserstein distances, because these incorporate the measure, if you have a very complicated geometric object that's added as noise, but that's very low measure, it won't change these very much. So they are very well adapted to these questions of robustness. This is a viable formal foundation for talking about these questions of robustness. And so this is one basic result. Now, this covering bifiltration is in principle not computable, if you remember the definition of that. But the degree Rips thing, D, is. And what we prove for that is that if it's a little bit more complicated, but if you take something that bounds the Gromov-Proorov distance, then you get an interleaving which shifts by delta in one direction and 3 in the other. And 3 is a unavoidable constant here. So this is a weaker bound than the one we get for this sort of filtration. And I'll say something about the consequences of that weakness in a little bit. But a corollary of this, so what is this? What kind of stuff does this buy us? One of the things this gives us is a law of large numbers that says that if you have convergence of metric measure spaces, then that implies convergence of the homological invariance associated to these sorts of bifiltrations. And so this tells us, for instance, that if you sample densely with high probability, you can expect to have a robust shape descriptor of your data. Okay, so let me now give you a concrete example of what this actually looks like on synthetic data. So, okay, so here's our example. So we have 3 data sets. We have X, which is a densely sampled circle in R2. We have Y, which is the same circle with a bunch of points added in the middle. And we have Z, which is the circle filled in essentially to be a densely sampled disk. And below are these pictures of what we get from the biparameter, so a 2-dimensional persistent homology associated to what I was denoting as the construction D. So this is from this degree Rips bifiltration. And the way to think of this is the gray region is where the homology in dimension 1 has rank 1. So a point in here, this is a particular choice of a density value and a scale value. And at this choice, we have rank 1. These purple lines, this is, remember, one way I talked about summarizing these is that you take a line through your parameters and you compute the barcode along that. And what we see here is that, let me get a different color for this, is that along this line, there is a 1-dimensional topological feature that lasts for that region of parameter space. Here, there's a much smaller one, and over here, there's none. So what the stability theorem tells us, what does stability tell us in this context? Well, if you look at this and this, these are close in the Gromov-Proorov or Gromov-Wasserstein metric, right? Most of the mass is on these points, and those coincide. And then there's just a little bit of mass in here. And so that tells us that the guarantee basically tells us how to describe some part of the region in here in terms of the part of the region in here. So we can connect those. So there's a relationship between this non-zero region where any line through that area is going to have value 1 for the first persistent homology group, which is, or vector space, which is detecting this circle. And over here, what we have is just a disk. And so there's no loop, there's no hole to detect. And indeed, this is not close to either of these things in these metrics. And there's no region here. And this is sort of, you can see, it's hard to tell from the colors on it, but there's no information in dimension 1, basically, except for except in the very far corner, there's a little bit of information. Oops, didn't want to do that. There's a little bit of information that comes from the fact that you get these tiny little circles connecting points, and that produces sort of schmutz in low degrees. What that looks like on the barcode is, you have these tiny little lines at very low feature scales when you've made these little loops that very quickly close up. Okay, so that's the theorem and something about it in practice. And I want to now wrap up by talking about open problems, because this theorem is, I think, a start, but we really don't understand this phenomenon in the way we need to in order to use this stuff practically in data analysis. I should say, while I'm here, these pictures and this analysis tool is a piece of software called Rivet that's due to Mike Lesnick and Matt Wright, and can be downloaded to play with. So now let's talk about open questions. So a key thing to do would be to get first question is to get a more geometric understanding of what robustness means. So if you remember, I gave, what was the theorem? The theorem was some kind of numerical result. This distance is bounded by this. But if you look at these pictures, there's clearly more geometric regularity, right? This is some kind of triangle. This is some kind of distorted triangle. One might hope for statements that were expressed in terms of the shapes of the regions in this multidimensional persistence space, these filtered vector spaces that corresponded. We see this in examples. There's a tremendous amount of geometric structure in the shape of this invariant, and we don't yet have the tools to say precisely what's happening. Another kind of thing that we don't understand at the moment is that in practice, the empirical stability that we see is much better than what the guarantees we get from our bound. So if you look at this part, I drew these red splotches here and here to indicate what the stability theorem was telling us, and that's not quite to scale, but it's pretty representative. The stability theorem sort of guarantees some correspondence and non-zero correspondence between fairly small regions inside these much larger regions. And the bound, as we have proved the bound, that bound is tight. And so you can construct perverted examples that are extremal for the bound we gave. But the question is, what? In generic cases, it's much better. And so some kind of theory of generic geometric objects here would probably lead to, on average, better stability bounds. And it would be very interesting to think about how to do that. Another thing, and one thing that I haven't talked about at all, perhaps shamefully, given that this is about big data, is that there's a tension between finding descriptions of these complexes that have tractable computational properties and ones that we can prove stability and robustness guarantees for. So for instance, if you look at this theorem, once again, we get a better bound for the B complex. That's a much nicer bound, but that complex is unmanageably large. Whereas this degree rips, the D complex, is much smaller, but we get this kind of weaker and bound with a constant of 3 that again is tight, that can't be removed. And what does it mean to be computationally tractable? Well, the cost of computing these homological invariants is essentially related to the cost of multiplying matrices. And so that's fine, but the scale parameter that controls the size of the matrix is the number of simplices, not just the number of points. It's the size of the complex. And the complex could have, if you think about it, could have exponentially many simplices, even in the case I gave, in the number of points. And these bifiltration complexes can become enormous. And this limits the scale of the kind of data we can apply this to. And so right now, there's this tension where the small computable bifiltrations we can't prove the very strong stability results for, and the ones that we can prove stability results for are currently uncomputable. Now, there's active ongoing work by many people to try to solve this problem, but I think it's a very interesting area. Another question is that, I pointed out that we don't get very good, invariance, we have these sorts of pictures, but we don't get very good invariance of the multi-dimensional persistence. In the one-dimensional case, we get these barcodes, and even barcodes, on the one hand, that's a metric space. On the other hand, that metric space has terrible properties. You can't meaningfully take averages in that metric space very well. It's hard to compute centroids, and the behavior of the centroids can be pathological. And so there's a lot of work on, supposing you wanted to apply these topological descriptors as features that you then feed into some standard machine learning pipeline. You can't do that directly without somehow embedding them in a vector space or a Banach space or something, embedding them in Euclidean space. And so there are now many methods for vectorization, for producing maps that put these things in vector spaces, and these all have distortion. And we don't yet, I think, understand as well as we should, although this is, I think, much closer to being understood than these other things, maybe, how to integrate these kinds of strategies for turning these things into vector space valued invariance with these questions of robustness. And finally, and this is maybe nearest and dearest to my heart in some ways, is that there's a way of looking at everything I've described in terms of abstract homotopy theory, a theory of this sort of an abstract formalism for approximate homotopy equivalence. And it's very interesting because it has a different flavor than traditional homotopy theory because of this notion of approximation. And there's some relationships with shape theory and some relationships with sort of bounded and controlled homotopy theory, but it seems like a sort of slightly different angle on it. And I think people are just starting to understand things about what that abstract homotopy theory looks like, but we don't understand really how to describe this kind of robustness from that perspective yet. And I think there's interesting formal work to do there. But the take home, let me just finish by saying sort of the take home message from this talk in large part should be that there are these interesting multi-scale shape descriptors which capture higher dimensional shape information, and an active area of formal work to justify their use in data analysis is to prove that they are stable and robust in the face of perturbations of your data or noise. Okay, and I think that's it for me. So thank you for listening, and I'm happy to answer any questions you might have.
We have a Q&A box for the audience to ask questions. At the moment, I see it's empty. You can also raise hands if you want to ask a question verbally. Well, while people are thinking, a quick question from me is related to something you mentioned about these vectorization methods. Say if I'm interested in an application which is not from biology that you're focusing on, but do people use some of these topological data analysis methods to more obscure areas like text analysis, say? There is in machine learning, people are using word embedding method. Basically, clustering is really important in this area. So it has a natural connection to your methods. So I wonder what are the bridges there?
Yeah, absolutely. That's a great question. There are a bunch of different things you might try to do. So certainly you can use any of these sorts of embedding methods that put syntactic data, put words into a vector space, and then you get a metric. And instead of clustering it, you could do something like this. One of the interesting barriers to application of this. So I think that this is very promising. I also would want to be frank that a barrier to application of this is understanding what it means. Right? Clustering has the tremendous advantage that when you cluster when you do clustering for natural language processing, typically one hopes or believes, and sometimes this is more of a religious view than supported by fact, but nonetheless, one hopes or believes that those clusters have semantic meaning, right? Those clusters are, aboutness, that this is the cat cluster, and this is the cluster of stuff about it, economics, if you're doing document analysis or something like this. And there's been a lot of success on using that kind of idea. But here, the successful applications of topological data analysis are ones where you're working in low dimensions and you have a geometric hypothesis that explains what it means if you see a circle. Right. So, I mean, and this is, this is an issue, which is that if I tell you that, I took this text corpus and I did this, I embedded it in R50, and then I reduced it to R10, and then I computed homology. And, look, the 17th homology group has rank 10. You could feed that into a neural network and maybe it could predict, could solve your prediction task, whatever you were doing, but it's not clear what that means in any real way. And so, in places where this has been most successful, people have an explicit hypothesis about what kinds of shapes might turn up based on understanding of the process that generated the data. And so I think that in the case of text analysis, and I don't mean here to slander anyone, I don't know the state of the art, but a lot of the things I've seen, people have looked for interesting structures in text and found geometric structures, but I don't think there's a good generative hypothesis about what that should mean or why that would be there. Whereas in contrast, like there's a nice application in biology that I'm fond of to detect horizontal gene transfer. And the idea there is that if we think of, an evolutionary tree, but if there's been some sort of cross-species gene transfer, then you get loops in the tree. And so now, H1 or persistent H1 is a great way to go fishing for features that describe loops. And you can connect the expected number of those things to, for instance, models from population genetics about sort of what the branching process looks like. So in those sorts of contexts, when you have this model, you know what the geometric features mean, and you can understand sort of when you expect these things to work. So that's the situation. That's the situation with text. I mean, there's been some interesting work on what are called tree kernels, where you want to put some sort of metric on parse trees, and then feed that into, again, you can feed that into these geometric structures. And again, I think we're at the stage where phenomenologically people see things, but I don't know if people know what it means. But yeah, you could anytime you have a metric, you can do this. And the question is always like, then what do you down the pipeline? What do you do? And I guess I should say the flavor of this is like exploratory data analysis. So that typically the way people use this is that you go fishing for stuff and then you try to sort of figure out why that was there and come up with some hypotheses. The content of this talk was sort of about making sure that the formal tools you need to make sure that you're not fooling yourself because your invariants, are so sensitive to noise that they bounce all over.
Thank you. That makes a lot of sense. We got someone who has raised his hands. Anna Sussman, please, you can speak now. Anna Sussman, you are allowed to talk now. Or can you ask your question by chat?
So there are a couple of questions also in the Q&A. Should I?
Right. Yeah. So the first question is just about the.
Yes, so I can send along the slides. The next question from Sandra. So that's a good question. So UMAP is basically based on a one-dimensional, just as you say, is based on a one-dimensional version of using homological invariant, using the homological information to do clustering, but to use it in a slightly more sophisticated way than the single linkage clustering that I described, where you have sort of probabilistic inclusion of simplices. So I think that, I think that one could imagine doing a higher dimensional version of that, using sort of more homological tools. But I think the thing to say in answer to your question is that I haven't looked at it personally, but yes, that's a that there's a definite and strong connection there, and I think there's interesting stuff to do. And let's see. The next question is about data analysis alone or combined with machine learning. I think that the answer, of course, is both. As I was commenting before, the issue for machine learning is that you want to, well, one is that you want to make sure you have stable features to put into that, but two, you often would like, I mean, the promise of geometry is that one of them is that it might be interpretable and let us make sense of our data. And to the degree that we just use this as uninterpretable features for machine learning, you can do that, but it maybe seems to me, and this, again, I should say this is a religious viewpoint, that seems less satisfying. Okay, any other questions? Okay.
Yes, thank you very much. Let's then.
So much. Let's see if
Thank
we
you.
have, I don't know, let's get some applause and reactions and things in the chat. All right. We're running a couple of minutes late, but let's take a 1.5 minute break and we'll reconvene at 05. So people have a moment to like get up, stretch, and grab caffeine.
May I share my screen?
Yes, please go for it. Perfect.
Right. Is that all right?
Perfect.
Great, thanks.
All right. Ready to get started? Awesome. All right. Continuing our slate for the first block. Our next speaker is Katrina Liggett. She is an associate professor of computer science, head of program on Internet and Society, and a member of the Fetterman Center of the Study of Rationality at Hebrew University. She completed her PhD in computer science at Carnegie Mellon and then did a postdoc at Cornell, and has been supported by a effectively uncountable number of granting agencies, but here are a couple of examples. The DARPA Brandeis Project, the Hebrew University Cyber Center, the NSF, she holds one of the prestigious NSF Career Awards, the US Israel Binational Science Foundation, Google, the Okawa Foundation, Microsoft Research, AT&T Labs, the list goes on and on and on. But even more impressively than that, she's just like an incredible contributor to many different branches of the computer science profession. She's been involved in organizing and leading in more conferences than I can count. And this list literally is uncountable. If you go to her website, it's just like massive. Most recently, was chair of Fork, and is a real leader in sort of the econ CS communities and the responsible computing and sort of fairness and as applied to learning and data communities and everything else. And then on a personal note, I've had the extraordinary opportunity to work closely with her for the past couple of years because she's been serving as secretary treasurer of the ACM Special Interest Group on Economics and Computation, SIG-Econ, where she is, it's just an incredible experience to work with her. She's like tireless and, super brilliant and super high efficiency on everything. Sort of gives me a lot to look up to and aspire to. So she is going to tell us about privacy as stability for generalization. Let's all welcome Katrina.
Thanks, Scott, for the very kind and somewhat embarrassing introduction. That's great. And thanks for having me, everyone. It's a pleasure to be here. So I'm going to be talking today about a problem that I view as really fundamental to doing science on data. And I hope I'm going to convince you that you have something to worry about here, but also that there's a community that's been making progress towards a toolkit that I hope in the somewhat near future might actually be practically relevant to addressing this concern. So I'll be talking today about a variety of papers of my own and of others. The joint work of my own is joint with Christopher Jung, Seth Neal, Aaron Ross, Saeed Sharifi, Melva Jardy, and Moshe Schenfeld. But I will try to give credit to others along the way because it's not just my own work by any means that I'll be talking about today. So the problem that I want to talk to you about today is what I'm going to call the data analysis, the adaptive data analysis problem. So the plan for today is I'm first going to tell you what I mean by this problem, try to convince you that there's a real problem here for basically anybody who does science on data. And then I'm going to introduce you to a framework for addressing this problem. That framework leverages a toolkit that typically goes under the name of privacy, and in particular differential privacy. But for today, this is not a privacy talk. Our goal is not privacy. Our goal is making good use of data. And then towards the end, I hope to have some time to hint a bit at where I think this area is going and what my hopes are for what I think it might be able to accomplish, and some hints at some open questions in this space. Okay, so the model that we'll be looking at today is one where we have some domain of data points, which I'll denote as scripty X. We have a scientist who has access to a data set composed of n such points. And the model is that, so the scientist is going to be developing a mechanism, M. And what that mechanism does is it needs to answer queries. And so the scientist has the data set, the scientist is fed queries, and the scientist needs to generate responses to those queries. We'll model those queries as coming from some scripty A, but if in your mind you prefer to think of the scientist as being both the one answering the queries and the one asking the queries, that's totally fine. Hopefully in a few minutes you'll understand why I sort of decompose it in this fashion. It gives us some insight. But basically think of it as the A is observing the answers to previous queries and is generating new queries, and the M is generating those answers to queries. So if you sort of wrap this all up in a box, you can think of this interaction between the scripty M, the scripty A, the mechanism, and the analyst as, given access to a database, what it does is it generates a sequence of query answer pairs. Okay. And what I'd like to argue is that this is a pretty decent abstraction for basically data-driven science, machine learning, statistics, but more broadly, doing science on data. And what's the concept? Well, the concept is that we often have in the backs of our minds that there's some true underlying distribution over data points or over data sets. But for today, let's talk about over data points. And what you want to do is you want to do science that pertains to that true underlying distribution. But of course, you don't have access directly to the distribution. What you have access to as a scientist is you have access to a sample from that distribution. And so you're constrained in some sense to do science on a sample. But what you hope is that this process of answering queries, somehow guided by the information you have from the sample, is going to give you results that have some significance for that underlying distribution from which the sample was drawn. I argue that that's basically what's going on when you do science. Is you're doing science on a sample in most cases. You don't usually have the underlying distribution, but you'd like the science on the sample to say something about that underlying distribution. So for today's talk, we're going to focus on queries that take a particular form. This is mostly for convenience, but I want to make sure you're comfortable with that particular form. There's something that we call linear queries. You feel free to think of them as statistical queries if you come from machine learning. Basically, these are queries that are identified by a query that can be issued on a single data point. And when we issue this query by analogy on an entire data set, what we do is we just respond with the average value across the entire data set. So you can think of these as encoding things like, what are the correlations between various columns in my data set? But just more generally, this is a very flexible and general class of queries that we're looking at today. Okay, and so what do we want from science on a sample? Well, like I said before, what we want is for it to say something about the underlying distribution. And toward that end, I'm going to give us now two definitions to start to formalize our goals here. So the first thing is not the goal, but it's maybe a tool towards the goal. And that's the thing we're going to call sample accuracy. So when I say sample accuracy, I mean the goal that the answers A that our mechanism gives to the queries Q that get issued ought to be pretty close in the sense that the queries, as if you evaluated them on the data sample, that should be similar to the answers that we give, and that's with high probability. So it's up to probability of beta that we have these sort of alpha closeness guarantee between the answers that we give and the true answers on the sample. But of course, what we really want is for the answers that we give to be close to the true answers on the underlying distribution. And that's what we call distributional accuracy. So that's in some sense a goal of doing science on a sample, is to give answers to the queries such that they're close to the true answers on the underlying distribution. You could formalize other goals, but I posit that this is at least one of the reasonable goals. Okay, so how can you get guarantees when you do science on a sample? Well, naturally, they should somehow derive from the fact that that sample was drawn IID, at least we hope, IID from the underlying distribution. So if we can set aside for the moment sort of the weirdness in that picture that I drew at the beginning, where that A that was generating the queries, that analyst that was generating the queries, had access to the history of previous responses to queries, set that aside and assume for a moment that we live in the simpler world in which, say, we just have a single query that's fixed in advance. The question is, how can we say something about how evaluating that query in the sample has implications for the underlying distribution? And of course, one natural way to think about this is via Chernoff bound, which basically tells us that, yes, indeed, with high probability, a query of this sort evaluated on a sample is going to be close to its true value on the underlying distribution because we've sampled from the underlying distribution. And similarly, if we had a sequence of these queries fixed in advance, and we wanted to answer all of them and say something about the probability that all of them are actually close to their true values on the underlying distribution, when we instead evaluate them according to a sample, we could simply do a union bound. And what the nice thing that we'd see here is that the number of queries that we can answer basically grows exponentially with the amount of data that we have on hand. So that K shows up inside a log. And so if you compare between that N, the amount of data points that you have, and that K, you can see there's an exponential relationship. So this is saying, if we fix a sequence of queries in advance, we can do amazing amounts of science on a sample. We can answer exponentially many queries and get good answers with high probability. So that's really nice. But now let's return to the model a little bit. In the model that we had at the beginning, the queries were generated as a function of the answers that our mechanism gave to previous queries. So first of all, why would I want to model such a thing? What is this adaptivity? Why is it maybe realistic? So I'd argue that adaptivity is really a fundamental aspect of how science on data works. At a sort of micro level, you can see adaptivity in the form of the scientist gathers her data, takes a look, or does some initial calculations, notices something interesting, and then digs in to see what's going on there. At more of a macro level, we see adaptivity in the form of one research group comes up with an amazing finding and publishes it, and then another research group builds on it, goes back into the data, and looks for something new. And particularly in settings, for example, like genetics, where there are large, valuable data sets that get reused across research groups, this type of adaptivity is really fundamental and really inevitable, that we see groups reusing the same data and building on the findings of previous groups or of the same group itself. This kind of adaptivity happens all the time when we're doing science on data. And what I'd like to convince you of now is that it can potentially get us into a whole lot of trouble. Okay, so I'm going to build this up with a sequence of examples. The first one should feel contrived. But first, I want to convince you, yes, there is some issue with adaptivity. So what if I allowed the query that gets issued to be a function of the data sample? The problem that could happen is that this would allow us to generate a query whose behavior on the sample is extremely different from its behavior on the true underlying distribution. And therefore, in some sense, we could mislead ourselves. We could overfit. So how do you do that? So one way to generate such a query that's very different on the data sample than on the underlying distribution is, well, if you have access to the data sample, you can just define a query such that every time it receives a point that's in the data sample that the scientist has access to, it returns a 1. Every time it receives some other data point that's not in the scientist's sample, then it returns a 0. And naturally, this is a query that performs very, very differently on the sample than on the underlying distribution, assuming the distribution actually has support elsewhere, in addition to where the sample does. And so you very, very quickly get to a situation where you've managed to identify a query that's not going to perform the same on the sample as on the underlying distribution. Okay, so fine. We knew it was the case that not all queries are going to perform the same on a sample as on the underlying distribution. And this felt somewhat sort of arbitrary. You know, we allowed the analyst to pick this terribly designed query. But of course, we know that's not how science works. Scientists aren't trying to mislead themselves by trying to ask queries that behave differently on the sample than on the underlying distribution. At least we hope they're not. So what if instead we say, okay, we're not going to design the query as a result of knowing something about the sample. We'll pick a query based on the answers to previous queries. That sounds a little bit more reasonable. But actually, we can get ourselves right back to the same place very, very quickly. What do? We issue a first query that encodes the data sample and its answer. And then we issue a second query that does what our previous query did and maximally gives us a difference between performance on the sample and performance on the underlying distribution. Okay, but again, that felt very contrived, right? Of course, scientists don't go around trying to issue queries that encode their data set and then use that to issue queries that get them in as much trouble as possible in terms of overfitting. So let's try to go somewhere a little bit more natural, but hopefully you're starting to get a little bit uncomfortable because you see the power of adaptivity. You see, as soon as we start to be able to issue queries that are chosen based on the answers to previous queries, that Chernoff bound no longer applies. You know, I said before, oh, wow, you can answer exponentially many queries in a sample and get great answers with high probability. No, once you have adaptivity, no, you can't even ask 2 queries and get yourself anything. Okay, but what if we make the analyst a little bit more reasonable, a little bit more natural? So here I'm going to break a little bit from my model as I've presented it so far, but just because I think it gives a very clean way of framing things. I'm going to do a very simple algorithm here, but you should look at it as this is an example of basically something that really does happen in the real world with machine learning, with data science. And of course, there are more sophisticated versions of this that basically do the same thing. So what's the setting that we want to look at for this example? Suppose that we have a scientist who is trying to do a classification task. For example, she wants to classify which images are of cats versus of dogs. She has access to a data set for training of labeled examples. So these are vectors of some d dimension that are also labeled with cat or dog. And what she'd like to do is use that to develop some algorithm that will be able in the future to label unlabeled images correctly. Okay, so what's one natural thing you could do? Well, you could try to figure out whether or not there's some features that you have in your data set that are very predictive. And you could try to leverage those predictive features. So in particular, this very naive approach, but really at the core of a lot of what we do in machine learning, is you could say, okay, let me identify the predictive features by saying, hey, they're the ones that have a correlation in my data set of a bit better than random. And then now I'm going to create my predictor on the basis of these predictive features. So maybe say I'll take a majority vote over the features that prove to be predictive on my sample. And that's going to be my algorithm. Now I'm going to deploy this to try to label cats and dogs. It seems like a very reasonable thing to do. The problem is, if I then were to evaluate the performance of this predictor, it would have extremely different performance potentially on my sample than on the underlying distribution from which that sample was drawn. And one way to say this clearly is imagine actually the data was just garbage. It was just random labels, random data. Well, if you have enough dimensions to your data, there are going to be some dimensions, some features that look predictive. And you're going to grab those and you're going to build yourself a classifier that looks pretty good on the sample, but it's just doing nonsense on the underlying distribution because the data was just random with random labels. So you can see that even here, where we did something that was kind of natural and reasonable and sort of has pretty good analogies and things that actually get done in the real world, we can get ourselves into trouble with adaptivity. And it wasn't because we were trying to encode the data set in our answers to previous queries, but somehow we managed to discover some aspects of the data sample that were anomalous, that somehow don't exist in the underlying distribution. And we managed to leverage those to create a query that's going to perform very differently on the underlying distribution than it's going to perform on the sample. So we have this sort of discomfort that adaptivity can get us in a whole lot of trouble. And it's not just us, and it's not just these cooked up examples. You probably all have seen that data-driven sciences are broadly in a form of crisis. And one of the issues that has been blamed for this crisis is adaptivity. And intuitively, what's going on here is as soon as you allow your choice of analyses to be chosen adaptively as a function of the results of previous analyses, then you have this ability to much more rapidly explore the space of possible analyses. It somehow sort of has this tree structure that you're exploring through. And so you can get yourself to the point where you can discover these overfitting queries much more quickly than if you did something non-adaptive. Okay, so what on earth are we supposed to do? One approach that's been taken widely actually in the data sciences is to throw adaptivity out the window, to say pre-register your studies. You have to pick all of your analyses in advance. Adaptively chosen analyses, we don't know what to do with them. No guarantees are available, so forget it, stop. Analogously, another draconian approach that really sort of is pretty harmful, I think, to making the maximal use of our data is to say, don't reuse data. For every question you ask, you have to gather a fresh data set. Now, feel free to be adaptive because you're not going to mislead yourself. You can look at the results of query 1 on data set 1, and you can use them to pick query 2 because you're going to issue query 2 against data set 2, freshly drawn IID samples. And so you're no longer going to be misleading yourself. It works, but it's also extremely costly. So now what we see is that instead of that wonderful world of Chernoff bounds where we could answer exponentially many queries in the size of the data set, now the size of the data set needs to grow linearly with the number of queries. This is a major blow. So adaptivity has really gotten us in a lot of trouble. Another tool that we could potentially use is if we could somehow guarantee that the output of our mechanism, so the results that we're outputting as we're doing our science, are actually not super expressive. They can't really fully encode the data sample, but actually they can be compressed to a small number of bits. Then that limits how much can be encoded there, and that can prevent a deterministic analyst, at least, from exploring too many queries intuitively. So we'd like to do something that's more general and better than this. And hopefully now I've convinced you that we really have a problem on our hands. Okay, so now what I'd like to do in the next part of the talk, which is really the meat of the talk, is to introduce you to a framework for addressing these concerns of adaptivity. So basically, intuitively, the argument is going to run by way of a triangle inequality. I'm going to start with a different and somewhat simpler and more familiar triangle inequality, though, to give you a sense of how this type of argument might operate. Okay, so what is this picture that I just put up in front of you? So what's our goal when we do science on a sample? our goal is at the top here. It's to, for all of the queries that get issued, give answers that are pretty close to the values of those queries on the underlying distribution. The bottom left corner is what we actually return. So we'd like somehow what we return to be close to that, Platonian ideal of the answer to the query. And what we're going to call that for this talk, we're going to call having those two things be close, our answer and the sort of true underlying answer, having those be close, we're going to call distribution accuracy. And so I argue one way to achieve distribution accuracy is by way of a triangle inequality. If we could guarantee that simultaneously the answers that we give are sample accurate, meaning they're close to the true answers on the sample that we have access to, and somehow we've managed to promise that the queries that are being generated are queries such that their answers on the sample are close to their answers on the underlying distribution, then we'd be fine. The problem that we have is that we don't know how to make sure that queries that differ wildly between the sample and the underlying distribution don't get issued. But if somehow we could get a guarantee that the queries are all going to be nice queries that behave similarly on the sample and on the other underlying distribution, we'd be done. We could just give sample accurate results, basically answer the queries according to the sample, and we would get distribution accuracy. So we're not going to do it exactly by this argument, though. The intuition is that the problem that we're facing here that comes from adaptivity is the fact that, or a problem that we're facing, is the fact that the answers to queries can encode a lot of information about the data sample, and that information can be leveraged in future queries. So if we could control how much information was encoded in those queries and how it was leveraged, then we could potentially get ourselves out of this problem. Okay, and so in order to sort of encode that intuition, what we're going to do is we're going to look at an object that at first blush looks a little strange. We're going to suppose that there was some interaction between the mechanism answering queries and the A that was generating queries. I'm going to generate a sequence of query answer pairs. Call that a transcript, some transcript pi. Now I want us to think about what does that pi encode about the data sample that we didn't already know if we'd known the data distribution. What is it telling us that's really specific to the sample and not to the distribution? Well, one way to think about what's being encoded about the data sample in our answers to a sequence of queries is to think about the following thing. Think about the posterior distribution on data sets that's induced conditional on seeing this transcript. So suppose you started with a prior that was actually the true distribution over data sets, and now you updated your beliefs about the data set that generated the transcript that we saw based on having seen that transcript, right? We're going to call that object, that posterior, that's conditioned on a transcript pi, we're going to call that q sub pi. And now what I'd like to sort of at least intuitively convince you of is that if we can say something about that q sub pi that can actually help us tie our hands and prevent us from encoding and leveraging too much information about the data set. And that can help us avoid this overfitting that's driven by adaptivity. Okay, so in order to do that, we're going to come up with two new notions of things we might want to guarantee. The first one we're going to call posterior insensitivity. And what does this say? We say that an interaction enjoys a guarantee of posterior insensitivity if it has the property that the queries that get generated by the analyst are such that their answers on the underlying distribution are very, very similar to their answers on this posterior distribution. So again, what is this posterior distribution? This is the posterior distribution that's induced by the transcript. So it's sort of how do your beliefs about the data set change having seen the prior transcript of interactions? And if we can guarantee that we have this guarantee that the queries that get issued are queries that behave similarly on the posterior to on the underlying distribution, that feels like progress. These are queries that somehow aren't leveraging too much of the information that was encoded in that posterior. And relatedly, we're going to also define posterior accuracy as saying we guarantee that the answers that our mechanism generates, those A's, are very, very close to the answers to the queries according to the posterior distribution. So if we could somehow give answers that are close to the answers on the posterior distribution and make sure that the queries that get issued weren't leveraging too much information about the posterior distribution, weren't causing us to answer queries such that the posterior and the underlying distribution behave very differently according to them, then we have this new triangle inequality. So again, we still want to get distribution accuracy. We still want the answers that we give, that's the lower left-hand box still, to be close to the true answers on the underlying distribution, that's the top box. But now we're going to argue it by a different triangle inequality. We're going to argue, well, one way to achieve this is simultaneously to get posterior insensitivity and posterior accuracy. So if we could somehow guarantee that the interaction between the mechanism and the analyst, the thing that's generating the queries and the thing that's answering the queries, if that interaction could simultaneously get posterior insensitivity and posterior accuracy, then we would be safe from the harms of adaptivity. And that's sort of a very trivial theorem once you write it as a triangle inequality. If you have a mechanism that's posterior insensitive and posterior accurate, then it's immediately distribution accurate. The question is, okay, so how do I get something that's posterior insensitive and how do I get something that's posterior accurate? This is where differential privacy comes in. Differential privacy is actually going to end up being a tool for us for achieving guarantees of posterior insensitivity. Okay, so some of you know what differential privacy is very well. To those of you, I apologize. I'm going to spend just 2 minutes giving the rest of us just intuition for what this is. I'm not going to go into any detail in the definition here. So what differential privacy is it's a notion of privacy for statistical databases. You can think of it as really a robustness or a stability guarantee on computations that says that the mechanism that you run on a database should be constrained such that when you run it on any two extremely similar databases, say differing in one person's information, that it should produce almost the same results, where almost the same results is in some particular formal sense. But let's not dig into the details here. I just want to give the intuition. So differential privacy is a stability notion that says changing the underlying database should produce not very different results. Why is this maybe natural as a notion of privacy? Well, what it says is that no one person's information in the data set is having an outsized effect on the results of the computation. And therefore, you're not going to be able to back out very much information about any one individual when you view the results of this computation. So the notion of privacy, which comes from work after work, McSherry, Nassim, and Smith, and also earlier work, has really taken off, especially in the sort of the past 5 to 10 years. It's seeing really widespread embrace in a wide variety of settings where people care about privacy for statistical databases. It's one of the areas that I work in, and there's been a lot of progress on understanding what computations can we do with guarantees of differential privacy and what's the impact on how much data you need and the accuracy guarantees that you can give for these computations. Upper bounds, lower bounds, there's been a lot of study in this space. But again, for today, we don't care about privacy for privacy's sake. I'm introducing this just as a notion of stability that's been well studied. Okay? And so differential privacy is just a stability requirement on a computation. And it's a stability requirement that has a couple of really cool properties. So the first property that I want to highlight is that if you perform multiple differentially private computations, you enjoy an overall guarantee of differential privacy that can be quantified. It degrades with the number of computations. And the first point is that this is true even if the multiple computations are adaptively chosen. So you can already see where I'm going with this in some sense, but differential privacy handles adaptivity in an elegant fashion. So that's really key. The second thing that's going to be crucial for us today is that when you do this composition of multiple differentially private computations, the guarantees that you get scale not linearly with the number of computations, but actually you can answer quadratically many queries. And so that, I'm really just flashing results here for those who've seen these things before to see the connections. If you haven't, don't worry. But the thing that I'm pointing to here on this slide is if you look at that cardinality of Q, the number of queries you can handle, you can see that it's inside a square root as opposed to that N in this guarantee. So we know how to answer a sequence of, in some sense, quadratically many different queries subject to differential privacy. Okay, and that's going to end up being really powerful for us when we leverage differential privacy as a notion of stability. Okay, so now back to our triangle inequality in just a minute. What are we going to be able to achieve? The final statement that we're going to be able to achieve, as I'm stating it here, it's from that paper that's joint with Jung, Neil, Roth, Sharif, Bajardi, and Schenfeld, but it builds on a beautiful line of work that actually started with the work Feldman, Hart, Potassi, Reingold, and Roth, a series of papers that they wrote, realizing that this notion of stability for differential privacy was useful in this context of adaptive data analysis. The bottom line theorem statement, though, is one that says that if you have a mechanism that you can guarantee is simultaneously differentially private, so stable in this particular privacy sense, and sample accurate for linear queries, then it immediately enjoys a guarantee of distribution accuracy. So it immediately gives you the promise that the answers, the A's that it generates there, are close with high probability to the true answers of those queries on the underlying distribution. So you've been constrained somehow magically by differential privacy stability to be unable to generate queries that overfit. So this is incredibly powerful. And to interpret this, to see why this is sort of an improvement over what we knew before, you have to invoke that realization that I had on the previous slide. The differential privacy allows you to answer quadratically many adaptively chosen queries. So we have a way to generate answers that are simultaneously differentially private and accurate for quadratically many queries. And what that means is that we can answer quadratically many queries with an immediate guarantee of distribution accuracy. And to remind you, okay, quadratic is not as good as the exponential guarantee for the number of queries that you could get if they were not adaptively chosen. That was the Chernoff bound at the beginning. But quadratic is a significant improvement over the linear number of queries that you could answer if you were constrained to provide new data for every single query. So what this is saying is that differential privacy lets you reuse your data. This notion of stability is actually letting us do something more with our data than we were able to do before. And I think that's a really interesting and exciting insight. Okay, so how do we get there? I want to give you sort of the flavor of the argument here, but I'm not going to have time to get into any of the details. So the proof sketch really goes by the analogy to that triangle inequality. It has two pieces. We want to show posterior accuracy, and we want to show posterior insensitivity. And how are we going to get each of those two pieces? It breaks down really neatly. So remember, the theorem statement says if you have differential privacy and sample accuracy, then you get distribution accuracy. And the way that we show that is by showing that sample accuracy implies posterior accuracy, and that differential privacy implies posterior insensitivity. So due to the limited time, I'm not going to be able to give a huge amount of insight into all the details of how this works, although it's actually really not that hard. It's, if I had another 20 minutes, we could totally do it. So differential privacy intuitively, how is it giving us a guarantee of posterior insensitivity? Well, intuitively, because what differential privacy says is that the results of a computation can't be very deeply affected by small changes in the input data, because it's preventing us from learning too much information and encoding too much information about the sample in the results to our queries. And so this is actually going to give us, through not terribly complicated argument, a guarantee of posterior insensitivity. The other piece of it is actually even simpler. This argument that sample accuracy immediately gives you a guarantee of posterior accuracy. And the key idea here is this sort of Bayesian resampling lemma. It's this realization that there are two sort of thought experiments that you can do that are basically, that actually result in the same distribution. So what are the two things that I want you to think about? One is you imagine that you sample a data set, and then you look at the transcript of query answer pairs that this data set induces. And you think about the sort of distribution over data set, transcript pairs that's induced by this process. Okay, that was one experiment. The other experiment that I want you to imagine, this is a little bit more sophisticated. You're going to sample a data set. You're going to generate a transcript of query answer pairs from the sampling. And then you're going to resample a data set from the posterior distribution that was induced by that transcript. Now, the claim is that actually the resulting distribution over transcript, data set pairs is identical. And so this Bayesian resampling realization allows us to show a relationship between sample accuracy and posterior accuracy. Again, apologies for not getting to dig fully into it, but hopefully this gives you a little bit of the intuition for how this works. So again, so we have this proof sketch that gives us the triangle inequality that allows us to show the differential privacy. It's really giving us a new tool for protecting against adaptivity. Okay, but I promised you that there was going to be a sort of like, so what's next, and where is this going? So that's this. And I hope that right at this moment, if you've previously encountered differential privacy, but you haven't seen the implications for adaptive data analysis, that you're feeling a little uncomfortable or a little skeptical. Because if you know about differential privacy, you know about it as this sort of paranoid, worst case, cryptographically minded notion. Differential privacy requires a guarantee that's worst case over all neighboring pairs of databases that differ by one person's information. It's worst case over all outcomes that are possible results of the mechanism. It's worst case over all data distributions. It's worst case over all analysts. It's an incredibly demanding notion of stability, which makes sense if what you care about is privacy, but it sounds like overkill if what you care about is protecting against adaptive data analysis. So I have a couple of answers to this isn't that overkill reaction. And one is, in some sense, no. There are lower bounds that show that asymptotically, in the worst case, differential privacy is giving you the best asymptotic use of your data set that you could expect, handling as many, asymptotically, as many queries as you could adaptively chosen queries as you could possibly hope to handle. On the other hand, that's a worst case statement still. And what you really care about when you do science on a sample is there's a real distribution that's out there. It's probably not a worst case distribution. I have an actual sample from that distribution. It's probably not a worst case sample from that distribution. And I'm going to do actual computations on that actual sample, which are probably not worst case computations. Can I somehow get better guarantees and answer more adaptively chosen queries in this non-worst case setting than the quadratically many that differential privacy is going to allow me in the worst case? And the answer is maybe. So I have two pieces to a maybe answer there. So one is in a paper joint with my student Moshe Schenfeld from NeurIPS the year before last, we show that indeed you can relax the notion of differential privacy to achieve a different stability notion that still gives you all the guarantees of protection against adaptive data analysis. It is formally a relaxation of differential privacy. It's a necessary and sufficient condition for getting these guarantees, but we don't show how to leverage it to actually get better results. And more recently, in an unpublished, as yet unpublished work that's now up on the archive, we give some intuition for how to leverage the non-worst case nature of the real data analysis task that you might have at hand. And the key piece of what we give in this paper is we show that actually really formally, mathematically, and very clearly, there are two pieces to the overfitting problem. The first piece is you can get yourself in trouble if you encode too much information about the data sample in your answers to the queries. But actually that alone doesn't get you into trouble. You only get into trouble if you then leverage that encoded information in your future queries. And we now have a mathematical language for formalizing and talking about these two pieces and how they interplay to produce overfitting, and how you can potentially control either or both of these pieces to prevent overfitting. So I feel like we're really making progress to understanding this sort of non-worst case to get ourselves potentially into a situation where we can make much, much better use of the limited data that we have. So bottom line, what did we learn? We learned if you have no adaptivity, you can answer exponentially many queries. If you have adaptivity, then all those guarantees go out the window. You can sample split, so you can gather fresh data for every single scientific question that you want to ask, but that sounds terrible. You can use differential privacy to get quadratically many queries, which sounds promising. And there's hope that you can do even better if you're in non-worst case settings. So I hope that this has piqued your interest, gotten you uncomfortable about adaptivity, and hopeful for the future. And I will leave it there. Thanks.
That was totally awesome. Let's thank the speaker. This is always a little bit complicated to do over Zoom. We don't even, especially with the webinar format, we don't even have a sort of direct applause mechanism. But we'll get some emotes in the chat in a moment. But first, let's are there any questions for Katrina? We have one in the Q&A box immediately. Question is from apologies if I mispronounce your name, questioner incidentally. Daniel Alabi asks, thanks for the great talk. Do we know if/why we can't do better than answering quadratically many queries with differential privacy like, but not necessarily differential privacy definitions, e.g. based on maybe just using mutual information?
Yeah, so if you're talking about the worst case, the lower bounds aren't specific to differential privacy. So the lower bounds are really fundamental limitations on how many adaptively chosen queries you can answer. So if you go back to those lower bound papers, these are fundamental lower bounds. It's not specific to differential privacy. So you're not going to beat this with some creative sort of mutual information based stability notion. But again, that's worst case. And I feel like as a field, we sort of got caught up on these lower bounds and viewed them as really sort of insurmountable. And so we said, okay, differential privacy, it basically matches asymptotically. We're done, but we're not done. I really don't think we're done here because I really think that there is interesting work to be done outside the worst case. Thanks for the question. Great question.
Super slick. Any further questions? Let me ask a quick one. So, your opening did a very good job of terrifying me about basically every data analysis I've ever been engaged in. Is there intuition for like how we get to, how do we get to a world that is safe in the way that you're setting us up for?
Yeah, it's a good question. I mean, so the sort of pedantic answer is like, eventually we're all going to be injecting small amounts of tailored noise into all of our computations that, guarantee that we're not encoding too much information. We're going to have basically sort of devices looking over our shoulders that are going to be watching to see and warn us when we issue overfitting queries. They're going to say, haha, wait, you do not want to ask that question. Realistically, we're a number of years away from that world. The interim, I think, is going to be a difficult growing period because right now we have this sort of terror, which I think is totally justified, and we don't really have practical tools, both in the sense of practical, like, I can press a button and it's going to protect me from adaptivity, but also in the sense of right now, the tools that we have available are, sort of asymptotic guarantees that really only kick in to beat sample splitting on really huge data sets. We don't really have anything practically for you to do today other than feel really uncomfortable. And that's a terrible situation to be in. I agree. I'm sorry to be the bearer of bad news, but I hope that we're going to get to that sort of sci-fi world in not too many years, where actually there's going to be a framework around your analyses that's going to be protecting you from encoding too much information, but also sort of looking over your shoulder to tell you, hey, that query, that's going to get you into trouble.
Super interesting. Wow, that's fun to imagine, honestly, right? That, like, we might basically have like a query bot, keeping track of our analysis. That's super cool. All right, any last questions? You can ask them in the Q&A or in the chat, or hit the raise hand button. We'll do last questions going once, going twice. All right, sold. Let's thank Katrina once more. Please throw some thanks and appropriate emotes in the chat. I did steal that line from Twitch, but it seems to work out. And we will again take a 5-minute break before the next talk. And so we will reconvene. Actually, let me check what the official schedule is. I don't know whether we actually made out time. We will reconvene in, whatever, I can't find it quickly. We'll call us back to order at 10:58 and get, or 58 wherever you are, and get started. Thanks so much. Katrina, that was awesome. Thank you very much.
Thanks very much. Thanks for the invitation.
All right. Okay, cool.
Katrina, when you were talking about worst case can be too harsh, I know that the computer scientists love worst case scenarios, but I thought you would be going into the direction of what statisticians are looking at, basically type 1, type 2 errors. And
so the thing that I'm critiquing here in the worst case is saying that differential privacy is overkill because what it's doing is it's really sort of in a draconian fashion preventing you from encoding too much information about the sample in your answers. But it's maybe adding too much noise to do this given the actual data that you have. And it's also not in any way leveraging the fact that maybe you're not actually going to issue a worst case next query that is going to maximally leverage the information that's been encoded. So it's a bit of a different stepping away from worst case than sort of what you alluded to. It's more trying to understand how can we say something about situations where the data sample and the data distribution and the sequence of queries don't sort of exhibit maximally sort of challenging attempts to sort of force us to overfit. But it is true that there is, in some sense, a trade-off here encoded in all of these results, which is a trade-off between you add noise to results and it makes the answers less correct, but you add noise to your results in order to make the answers more correct, in order to protect yourself from being misled. But that dance between those two is sort of encoded in the theorem statements already. Thanks for the question.
it's just that in statistics, when there is a problem of sequential data, I mean, there are ways to deal with it. You just account for how dependent the data are. So I wonder if it's possible to account for this dependency between queries. and again, get away from this worst case.
I'd actually love it if you could send a couple of references to what you're talking about. I think it may be a literature that I'm not familiar with, not coming from statistics. So if you don't mind, I'd really be glad. I think it's entirely possible that there are relevant tools hiding in places that I just don't know where to look. So I'd be really glad.
Yeah, it's very classical, so I'm sure you've heard of them, but yeah, I'll send you something.
Okay, thanks. I appreciate it.
Awesome. All right, maybe one more minute. Hima, do you have slides you want to load up?
Yes.
Sorry, we're running a couple minutes late.
Should I share my screen and test it, Scott?
Perfect. Let's do it. Perfect. Looks good.
See the transitions. Okay.
Cool. All right, ready to go?
Yep.
Perfect. Rock and roll. All right, everybody. Thank you for sticking with us to the second, quote unquote session of the conference. Our next speaker is Hima Lakkaraju. She is an assistant professor at Harvard. She's my colleague at the business school and also in our Department of Computer Science. And she leads the AI for Life research group and recently co-founded the Trustworthy ML initiative. She holds a PhD in computer science from Stanford. She's been funded by the NSF, Google, the Data Science Initiative, and Bayer. And she has published incredibly widely. She might be one of the only people on the planet, I believe, to have published in both NeurIPS and the Quarterly Journal of Economics. These are, sort of, I'm sure everyone on the line knows NeurIPS is, sort of one of the absolute top conferences in machine learning and AI. The Quarterly Journal of Economics is one of the absolute top journals in economics, and there's not a huge overlap between these research communities. And more broadly, she's published in many different computer science venues and other application areas as well. And then the other thing I should say, I mentioned she's my colleague at the business school. She joined a little bit after I joined the business school. I had the opportunity to help recruit her. And I don't know if I told you at the time, but like all of the background chatter was like, oh my gosh, we have got to bring this person to HBS because she's going to be like so transformative and innovative and so forth. And I could tell you my prior was super strong, but it's actually moved upwards, even from that high baseline. So we are particularly excited to have Hima here talking about a path towards reliable and robust model explanations. Let's welcome her. We'll applaud. Again, we're in webinar mode, so I'm going to applaud and everyone else will be applauding in front of their computer screens. Go for it.
Thank you so much for that intro, Scott. Phew, that's high praise, and I will try my best to not disappoint anyone here. So thank you again for having me here. Welcome everyone. I'm glad to be here and discuss some of our latest research with you. So today I'll be talking about explainability. I'll talk about what does that term mean and like what is the state of the art literature a little bit, what are some of the existing challenges and some of our recent work that tries to address a subset of these challenges. So one thing I just want to point out is it would be hard for me to monitor the chat as I'm giving a talk, but happy to take any questions like at the end. Feel free to like keep them coming in the chat. Okay? Thank you so much. All right, let's look at some high level ideas here, or like let's zoom out and look at the high level picture here, right? So we are all familiar with settings like healthcare and criminal justice and so on, where experts like doctors and judges make a lot of decisions today, right? Of late, there has been a lot of emphasis about deploying or at least considering the deployment of machine learning tools in these kinds of domains, right? So whether it's healthcare, using AI to help doctors with like disease diagnosis, treatment recommendations, or even early detection of certain diseases. When it comes to justice, like there are codes and systems that are trying to use AI tools to, of course, use them as like an assist tool for the decision makers in those domains. As ML is being increasingly deployed in these domains, or at least being considered for deployment in these domains, one of the key attributes to think about is that of interpretability. Right. So if we want a decision maker to leverage the decision or the prediction made by the machine learning model well, then obviously we want to sort of also make sure that the decision maker is understanding the rationale or the reasons why the model is making a certain predictions, right? So something as simple as what features is the model relying on when making this particular prediction. That understanding can be very helpful for a decision maker to think about, okay, is this decision being made by the model based on reliable and relevant features? Or is the model using some, complete spurious set of features in making this decision? And based on that, they might think differently about how much to rely on the decision of the model when making their own final call, right? So what is the status of interpretability in machine learning? Okay, so one thing that I'm sure several of you are familiar with some of these models, but basically there is a generic implicit agreement that simpler classes of models are easier to understand, right? For example, linear models, shallow decision trees, simple rule-based models, as long as the complexity of these models or the number of features they're using, number of levels in a tree, as long as that is not completely blown up, there's generic implicit agreement that shallow trees, linear models with fewer non-zero coefficients and so on, these are relatively easy to understand because they at least give some intuition into how the features are being used, what features are being used when making decisions and so on. But as we are seeing more and more, the tasks in the real world today are getting more and more complex. The data sets are getting more and more high dimensional and also huge, right? And because of all this, we are observing that complex models are achieving comparatively much higher performance. For example, deep neural nets are all over the place these days. Ensemble models like random forests, booster trees, and so on, they are being used more and more compared to simpler models, which are probably slightly more easier to understand, right? So what is the solution here? The solution that machine learning community more broadly has come up with is that let's first build complex models. So let's say there is a task, build a model as complex as you want to make it to be and as accurate as you want it to be. Then post hoc explain such models using simpler models. Okay, so that is the rough sort of the idea that gave rise to this whole field over the past few years of post hoc explainability. Okay, so today I'll be discussing about these three pieces. I'll first talk a little bit about post hoc explanation techniques, give you some intuition about some of the basic post hoc explanation techniques, talk about some of the challenges that are known with respect to these techniques, and then discuss our recent work, which tries to address some of these challenges, and then conclude with some interesting future directions and so on. Okay. All right, let's talk about post hoc explanation techniques, right? So these techniques typically consider a complex model as almost a black box, right? So these techniques often think of it as there is some kind of a complex black box that I don't need to have a complete understanding of, that I need to explain. So that is the perspective of how we think about when we try to explain a complex model using a post hoc explanation technique. So several of these techniques in literature require little to no internal details, knowledge of little to no internal details of the model. They pretty much read query access, which means you throw in a data point at the model and the model should be able to give you a prediction. Or at the most, a lot of these require like gradient access. So we should be able to know what, or rather at least compute the gradients of these models, right? So that is the level of access to the underlying model that they require. In a lot of the cases, you don't need to know the exact functional form. You don't need to know, I guess for computing gradients you do, but like, you don't need to know a lot more details about the model itself, right? So there are several post hoc explanation techniques, at least broadly, they have been categorized as local versus global approximations. So local, which is basically trying to explain the rationale behind an individual prediction. Global, as the name suggests, trying to explain the complete behavior of the model in some form or the other, right? And then there's also gradient-based versus perturbation-based techniques. And in gradient-based, as the name suggests, the explanations are computed computed by relying on gradients or by calculating gradients. Perturbation-based methods, they rely on perturbations or like small changes to existing data points in the data. So those are basically the computational differences, or a characterization based on how explanations are computed. And just to name drop, examples of some very popular post hoc explanation techniques include methods like LIME, SHAP, Muse, integrated gradients, GradCam, and so on and so forth. So there are several of them. So today we'll be focusing a lot on methods like LIME and SHAP. Specifically, I'll be talking about LIME, which is a perturbation-based method, and I'll tell you in a little bit why that is. And a lot of what I discussed today applies to this broad category called perturbation-based post hoc explanation methods. So LIME, right? So this method is model agnostic, so it requires just query access. We should be able to throw in a data point at the model and then get a prediction. That's all. No access to internals required, no access to gradients required, nothing. So the goal of this method is to generate local explanations, as I just suggested earlier, which means we try to explain individual predictions of any classifier by learning an interpretable model locally around each prediction, right? So how is the model making a single prediction? So that's what LIME is going to try and explain. And what is the output? The output here will be feature attributions for individual instances, which capture the effect or contribution of each feature on the black box prediction, right? So the output of this method would be something like a vector or like a list of feature attributions, which tell us which features are being used the most when making a particular prediction. Okay. Sorry. All right. So how does LIME do this? Or rather, what is the intuition that is being used for constructing these kinds of local explanations, right? The intuition is rather simple. The intuition is that while complex models have very complex nonlinear decision surfaces, for example, as you can see here, there's a light blue region and then there is this light pink region. So the decision boundary of this complex model is rather nonlinear. The idea here is that while that complex nonlinear boundary might be hard to explain to a human in a simple enough manner, if we zoom in enough and look at local pockets of the feature space, for example, the space around this particular data point here, you can see that even complex nonlinear models behave locally in this local neighborhoods, right? So linearly in this local neighborhoods. So for example, even though this decision surface is nonlinear, here you can see that it's almost like you can fit a linear model and try to approximate the behavior of the model there. So that is the intuition being exploited by LIME and also several other methods in the post hoc explainability literature. So what exactly does LIME do? LIME essentially does a very simple thing. It takes a point, let's assume that this is this red plus mark on the screen, takes a point, perturbs it slightly a number of times and generates a bunch of points around a given point, okay? So now we have a local neighborhood of that point, and then it fits a linear model like a logistic regression or a linear regression, depending on the task, in order to predict the predictions of the underlying complex model, right? So you're trying to fit a local linear model to approximate the local behavior of the underlying model. So it's a simple idea, and it works kind of reasonably in practice, of course, with some caveats, right? So there are several methods of how to perturb a data point and so on, and it goes anywhere from adding some random noise to more complicated techniques and so on. I'll not go into all that due to time constraints. Okay, so here is what LIME explanations look like. So on the top, what you see is basically a structured tabular data set, which is called the compass data set. It captures information about recidivism data. So we have fit a model to that, and we were trying to predict, person's risk or likelihood of committing crimes and so on. So here we see that, and we try to explain one prediction using LIME, and what you see is that misdemeanor charge, for example, has a feature importance value of about like 0.225, and green indicates like positive feature importance. Female has like a negative value of feature importance and so on. So it's giving you like point-wise estimates of feature importance. And it can also work on other modalities of data, like for example, images and so on. And here you're just looking at some of the top K, or like top 3 in this case, important features, right? So you see that the electric guitar strings is one important feature, and the face of this dog is an important feature, and so on. So this is the kind of outputs that line generates, okay? And here is the formulation. The formulation, so basically has 2 terms here. So one is the loss function, which is essentially trying to minimize the mismatch between the predictions of the underlying model as well as the explanations local linear model that you're trying to fit. Okay, so F is the underlying complex model, G is this local linear model, and then there is the pi of X, which is essentially like the neighborhood of X, right? We are trying to sort of fit a linear model that tries to match predictions as much as possible with the underlying complex model. And this term is basically trying to minimize the number of non-zero weights in the local model that we are trying to fit, the local linear model that we are trying to fit, because lesser features with fewer non-zero weights means that it's easily interpretable, right? So we want like a less complex linear model. Okay. And here, with respect to this loss function that we have here, this is how it's almost like a weighted loss function. So where the weighting is basically done based on how far off a particular perturbation is from the original point. So X is the original point. Z is basically the perturbations, which you can generate by adding some small random noise. That's one way. But the way to think about it is that this function forces that points that are farther away from X are given lesser weightage, whereas points that are closer to X are given more weightage, so that we are actually fitting like a local linear model here, right? So that's the goal of this function. Okay. Challenges. So what are some of the challenges? So the first question one might want to ask is, are line explanations even faithfully capturing the behavior of the underlying models, right? It's a valid question because at the end of the day, this is trying to explain what's going on. In order to do this, so people have come up with an array of metrics, each of which has its pros and cons. I'm going to talk about one specific metric here. A popular one is basically thinking about computing weighted R square on the generated perturbation. So line already is generating a local neighborhood. Now compute some notion of either weighted accuracy or weighted R square on the neighborhood that line is generating, right? What is the problem with that? So this kind of an evaluation approach has been critiqued quite a bit because it's dependent on the perturbations generated by line itself, right? So you're making your evaluation measure dependent on your method. So there are a lot of arguments calling this out as an unreliable measure and, you know, something that we should not use and can't trust, right? So there are also some other measures, but none of those are foolproof. So there is no very clear, reliable, winning way of saying, okay, this explanation is great and much better than this other explanation. So that's one of the ongoing sort of struggles with the field, and it's an open problem that needs more rigorous solutions. Another problem with methods like line is this challenge of lack of stability. And what do I mean by that? So if we take a small point and perturb it very slightly and generate like almost an infinitesimally close point, which does not affect the behavior of the underlying model like in any way, even then methods like line, you see that the explanations are somehow drastically different. So if you take a point, make a small change, ideally that change is not affecting the underlying model, but it still seems to affect the explanations drastically. And methods like LIME and also other perturbation methods, they have been shown to suffer from these kinds of problems with stability. There is another notion which is called consistency, and I know that term is overloaded, but in this context, when I say consistency, what I mean is when you take a data point and you run LIME repeatedly for a number of times without changing any parameters, there are several instances where you see that the explanations themselves are different. So you don't change anything, you're just like rerunning these methods and you see that the explanations are different. If you look at this particular picture, that picture number C, the picture C that I'm pointing at, what you see is that if you repeatedly run LIME on a particular data point, there are several blue lines that show up here. Each blue line is a particular explanation. So there is this whole band of explanation that is being traced by the method by just rerunning a method, right? On the same point, same parameter settings, everything. So one could see here that, with fewer samples, this problem worsens. With like many samples, this problem sort of gets better. So you could argue whether this is an issue with just having too few perturbations. Then the next question that comes up is, what is the optimal number of perturbations? Or can we just use a very, very large number of perturbations, right? The problem with that is we ideally cannot use a large number of perturbations like an infinite sample or a very large number, because querying complex models like InceptionNet or ResNet or AlexNet, which these approaches try to explain the predictions of, is extremely computationally expensive. So when you query such models repeatedly for labels of various perturbations, it can get prohibitive very fast and hamper with the actual practicability of deploying these kinds of approaches, right? And larger number of perturbations essentially means larger number of queries. So it's not a practical solution to just like use a very, very large number of perturbations. So what is the optimal number of perturbations? Nobody knows. And that's not a solved problem until this work. So generating reliable explanations using LIME can be computationally expensive, and all these challenges basically complicate things, right? So what do? So we have a solution to at least some subset of these problems, and the solution basically thinks about making this point-wise estimates of feature importances, removing them or like replacing them with feature distributions, right? So what do I mean by that? Instead of giving a vector of like point estimates of feature importances, think of it as like we have a distribution over the feature importances. So earlier you could see that these were the feature importances output by line. Okay, so for example, here it's saying with 100 perturbations, misdemeanor charge is like 0.225 or something. And then here you can see misdemeanor charge has gone back to 0.10 at 2000 perturbations. So there is some conflict. It's hard to kind of keep these two views and like see how they sort of kind of work with each other, right? Whereas if you look at like distributions, you will see that this view, like with 100 perturbations, you see that the uncertainty is much higher, whereas with this 2000 perturbations, the uncertainty is like much lower, and things are sort of much more certain, right? And you can sort of put these two views together because misdemeanor charge is kind of still within this bigger the belt of uncertainty here, and it still falls within that region. So there is no inconsistency between how to think about explanations, fewer perturbations with larger number of perturbations, right? To do this, what we do is basically construct a Bayesian locally weighted regression, which can accommodate the Lyman-Sharp weighting functions. And what is going on here is that, let's say Z is a perturbation and then Y is the corresponding black box prediction. So we model Y conditioned on Z, phi and epsilon. Phi is the feature importance vector, the mean feature importance vector, and epsilon is this nice term here, right? So we model this probability distribution as we sample this from this phi transpose Z plus epsilon, where phi transpose is a vector of feature importances that we will estimate, and then Z is basically the perturbation vector, which we will generate using sample schemes like adding random noise and so on, just like Lime or Sharp does. And epsilon is modeled as this kind of noise term, which includes this weighting function that has been employed by these prior approaches, right? And of course, like these are the priors on the feature importances, and they capture the feature importance uncertainty. But using conjugacy results, what we find is that we can have the following posteriors, and we can compute all the required parameters in closed form. For example, like feature importance mean can be computed as this equation, and we find that like this importance mean actually coincides with the mean computed by Lyman-Sharp. So in some sense, we are retaining the good things about some of those techniques by ensuring that these Bayesian methods correspond to those methods at their means, but we are also adding additional information on top of that, right? So there's measuring like two kinds of uncertainty. One is the uncertainty associated with feature importance is phi, and this can be obtained by basically computing the posterior mean using a closed form solution as given by this equation above, and then obtaining the credible interval around it by repeatedly sampling from the posterior of phi. And then there's also error uncertainty, which is basically the uncertainty associated with the error term, which captures how well our explanation models the local decision surface of the underlying black box, right? So those are the two kinds of uncertainty that we are trying to capture. And another sort of interesting piece with respect to explainability literature that is done in this work is to estimate the required number of perturbations in order to generate explanations that satisfy user-specified levels of confidence. What do I mean by that? Let's say a user comes and asks us that she needs an explanation where the true feature importance lies within plus or minus 0.5 of the estimated mean values with 95% confidence. Then we have a theoretical result which basically uses those as inputs, plus or minus 0.5, the width of the interval as well as the desired confidence, and then computes the number of perturbations needed in order to give an explanation which satisfies those certainty requirements, right? And that can be extremely useful in practice. And beyond all of this, we also tried to improve the scalability of these kinds of approaches. As I mentioned earlier, one of the big challenges here is that querying these complex models repeatedly can get very costly, very fast, and it can completely bring down the system. We may not be able to explain the points as we want to, and so on, right? So one of the solutions with this Bayesian framework is that instead of sampling perturbations randomly, like it was done with Lime and Shep, and then querying the black box on all those random perturbations, we choose the points that the learning algorithm is most uncertain about and only query their labels from the black box, right? So we are trying to do like a more focused sampling here, which also helps with the scalability aspects. All these pieces put together allow us to construct explanations with user-defined levels of confidence in an efficient manner, right? So we have the uncertainty associated with each explanation captured. We also have the minimum number of perturbations required to reach the desired level of uncertainty piece as well, and then improving the scalability of the sampling process as well. So these three pieces put together can be extremely useful in improving the practicability of today's explanation methods. I'll talk a little bit about some results here. And the first one is we were trying to sort of evaluate how good are the uncertainty estimates that our approach produces, right? And to this end, we compute what fraction of true feature importances fall within 95% credible intervals. And in order to get a handle on these true feature importances, what we do is we compute those by running methods like Lam and Shap for a very, very large number of perturbations. Like for small data sets, 20K turned out to be a large enough number, and we ran it for much more, but basically at some point the explanations reach a stable point, right? So we are basically seeing how would the explanations at convergence match with the explanations output with the number of perturbations as kind of computed by our approach, right? And here the idea is that the closer the values are to 95, the better. And what we see here is that for several popular and large-scale data sets like ImageNet, MNIST, Compass, and German Credit, some are tabular, some are images, these intervals are like pretty nicely calibrated, especially for Bayes Lime. You see that roughly they revolve around that 95% mark. For Bayes Shap, we see that these intervals are a little less well calibrated. Probably, or rather our hypothesis that we are still testing is that this is due to a concept of background distribution that like Shap uses. And we think that that is what is choosing that appropriately or choosing that a certain way can cause less calibration versus more. So that is the idea. But essentially what we see is if somebody requested us for an interval where our true feature importances would fall within that interval with 95% confidence, we would actually we are observing in practice that that is what is happening. The true feature importances are falling within our intervals with like 95% confidence, right? Another thing that I talked about is the stability, which is, making a very infinitesimally small perturbation to a point, which does not affect the behavior of the underlying model, should not change the explanation drastically, right? So that's a desired property. And we observe that methods like ours, which have this modeling of uncertainty incorporated in them, they are much more stable than methods like Lime and Shap, which were previously proposed methods. For example, on several data sets, you observe increments or like increases in stability of anywhere going from somewhere on an average of like 30–40% all the way up to like 70%, right? So we are seeing a huge improvement in terms of stability. And we also did some user studies just to see how users are able to think about the explanations that we produce versus some of the other methods before us do. We did one experiment. I'll talk about one experiment here. There are more in the paper, but basically one question that we wanted to ask was, are Bayes Lime explanations better than Lime explanations? And to this end, what we did was take a bunch of users, assign them randomly to Bayes Lime or Lime, Bayes Lime being our approach. And each user is basically shown a digit where the important features in that image of the digit are masked, right? And these important features are either given by our approach Bayes Lime or the baseline line, right? So you show a user an image where the important features according as deemed by the explanation are masked. And now the user's job is to recognize the digit in that particular image, right? So the idea, the intuition here is that the better the explanation, the more difficult it should be for users to get it right when the corresponding top features are masked, right? The more meaningful your explanation, the more difficult it should be for somebody to recognize the digit when you remove all those meaningful features. And what we observe is that the user error rate was 25.7% for Lime, which is the baseline, and 30.7% for Bayes Lime, which is our approach, indicating that users are having a little more trouble recognizing the digits in the images when the features output by our explanations are being masked, right? Like hinting that there may be more information in the features that are provided by the framework that we have. Okay, so thus establishing that Bayes Lime explanations are turning out to be more informative than Lime explanations. All right, so with that, I will summarize and give an overview of like what we just talked about and touch upon some important open problems in the field. So this work is one of the initial solutions which addresses some well-known critical problems with post-hoc explainability literature, namely fidelity, how faithful is a given explanation or how accurate is a given explanation, stability, consistency, and scalability, right? So these are all like some of the key issues that popular post-hoc explanation methods struggle with. And this is one of our first attempts to try and hit at some of these issues and hopefully address them a bit. And this novel Bayesian framework for capturing the uncertainty associated with local explanations. And we leverage these uncertainty estimates that are output by our framework to compute the number of perturbations required to generate explanations that satisfy user requirements in terms of what level of uncertainty is needed for a particular user in their explanations, and to also generate explanations more efficiently, right? So I want to kind of leave you all with like few critical pieces to sort of think about as I'm closing this talk. The first one is there is a real need to rigorously evaluate explanation methods today. So when I say that, there are basically two aspects to it. Thinking about are the explanations that we are generating faithful to the underlying model? What is a very rigorous evaluation framework to check that? Then the other thing is, are the explanations that we are generating actually understandable to the user, right? So the two pieces, I think there's a real need for rigorous evaluation frameworks there. to check both usability aspects with respect to if a user is able to make any sense out of a given explanation, and also if the explanations are actually doing what they're supposed to do, that is accurately explain the underlying model. The second thing is improving the reliability of explanation methods is key. As we talked through during this talk, there are several pieces where existing explanation methods don't really sort of work well. So fixing them piece by piece, and there's a first step, but like going forward and like not stopping working on this problem would be critical for making this field useful. And then the last one is, so far we are mostly still thinking about very elementary one-shot explanations where something is given to the user and that's about it, but thinking about a more interactive and a dialogue-based approach to sort of explaining these models is also going to be very, very useful. Okay, so with that, I think I will stop here and take any questions. Thank you so much for having me again. And here is the link to the paper. Thank you.
Awesome, super cool. Again, let's thank the speaker. We'll applaud and we'll do some emotes and stuff in the chat after Q&A. But first, are there any questions? Reminder, you can submit them via chat, via Q&A box, or hit the raise hand button. Maybe I'll ask one while we're warming up the audience. So this is super cool, by the way. You're actually, gosh, I have two questions. Can I ask two? I'm going to abuse my position as moderator, ask two questions totally unrelated to each other. So the first of them is about how, like, we should think about the parameters coming out of an application that basically go into your objective, right? Like you're tuning these, like how many, sort of how many perturbations do you need? Like, but how should we decide how much consistency we actually want to go after? And
yeah, I mean, yes. So I think one of the reasons why explainability is, I think, kind of, it's not a one size fits all answer is because the notion of what is explainable and what is required, I guess, changes with different contexts and different applications and so on, right? So that's why there is a huge tussle on like, what is a definition of explainability? Why can't somebody just give me a definition? And that's where it gets like trickier. But with respect to consistency, again, the term as we are using in this talk, which is essentially if you run the same method with the same parameter settings on the same point, you should get the same explanation. I think that need is something that we have seen is true across a lot of applications. Like I work with these applications with like medical data or like folks from medical domains as well as like policy and so on. But wherever you go, I think this need for consistency, which is if I run something, it better give me something that sort of like agrees with what I got on the first run, when I run it the 10th time, right? So that need is one of the few things that is like commonly holding across several applications.
that makes sense. Okay. No, it's super fascinating because like I'm trying to figure out, how I would, sort of how I would decide like what my internal trade-off in the objective is, for using these types of methods. But I guess you're right. You basically have to be in whatever the application space is and just sort of decide as a function of like, sort of how much risk you're taking. You might be much more concerned if it's a health application than if it's like,
That's true.
urban planning or something.
That's another great point. I think I can, just to kind of elaborate on this, I can give one more example, which is if people have been thinking about, should we give some rudimentary forms of explanations in the context of recommender systems, right? Like maybe Netflix or like Amazon products and so on. And for them, the challenge is they want scalability more because the data dimensionality and the space they're operating in is huge. And even if the explanation is not perfectly right, like that's okay. Like you can tolerate a higher degree of uncertainty, for example, right? Whereas if you look at medical domains, you can't tolerate too much uncertainty. So you want explanations that are going to have like much less uncertainty. So I think those are like the two extremes in terms of the applications that I have encountered during my collaborations in terms of how to think about these trade-offs.
I love it. That makes a lot of sense, right? Like if you're Netflix, you don't really care whether you told somebody like you should watch this movie because you also liked a similar movie or because you also liked a movie with the same actor or actress, right? Like, that's sort of intuitive enough.
But you
That's
care
very
about
cool.
scalability a lot.
Exactly, you
can't
care about scalability a lot.
mess with your scalability, right? Yeah.
Super fascinating. Okay, my other category of question. So you mentioned at the very end this vision for a, where I was going, like in my head, during your talk, I was thinking like, could you do this with like a human in the loop, right? Could you sort of be like sort of doing like a, system where you're sort of fine tuning the explanations by like showing them to humans and asking like, do you know what's going on? And then like, can you interpret this? And then like feeding it back in or something. So you have sort of a sketch of like a, like an assisted learning or whatever explanation model. I don't know what the right term would be here, but it's something like that. Could you give more of a hint of how that might work?
Yeah, so I think you're almost touching upon like this last point that I was making, which is
Exactly.
about, sort of have interactive dialogue-based explanation systems, right? So that is, of course, ongoing work, including, I think some of our group is doing some work, and so are some of other amazing groups out there. And the sort of the way we are thinking about it, at least as a rudimentary step to that, is a user kind of tells an algorithm, the explanation algorithm, what kinds of characteristics are important for them, right? Like, for example, this is a very, very simple rudimentary example, but we want to make these complex constructs more complex. Let's say the user says, oh, anything where you see a race is being used for any subgroup of the population, like flag those sort of patterns or like, insights to me, right? And then, the model gives you one explanation, and then the user basically says, yeah, I care about things where race is being used, like flag those out. And then the model sort of goes back and recalibrates and then tries to sort of explain the approach sort of tries to explain this model globally where those patterns are sort of more prominently featured. And then, the user can like keep having this dialogue and like keep getting new explanations which sort of highlight what is important to them. So that was like some of our recent years work, and we are trying to make those constructs more and more abstract and like more and more complex.
Super interesting, because it also, like a framework like that also creates some opportunity to sort of teach the user that they might be missing things.
Yes. Yeah.
Right. Like, if every time you like say, no, I'm looking at the, the chimney, and the system's like, no, you should look at the bricks. It's like, yeah, so cool.
And I think one of the uses, and I also understand that I think this is probably a more practical talk compared to Katrina's amazing, theory talk earlier. One of the important things of something like this is exactly what you just said, right? So which is, in practice, if a doctor, like I work with Brigham and Women's and MGH doctors and so on to try and test if these things are of any use to them. And one of the things is when we applied this on some sort of like scan data, X-rays and like CT scans and so on, for like cancer patients, we observed that there are some models out there which are actually considered as good authoritative models to parse these kinds of data. They were looking at things like, there is like a sort of a slot at the top of the X-ray, which apparently happens in some X-ray machines. And they were sort of using those to make these predictions. And to us, it was like a very mind-blowing thing, like, oh my God, these methods which are so popular out there, and people are thinking, yeah, this is a tool for analyzing or like understanding X-rays and making, predictions based on them, are using features that are completely off the chart. Like, it's, not trustworthy. Nobody should ever say, based on the type of the X-ray machine and the kind of thing it's producing, if there's a particular mark on the top right, then I'm going to classify this as having a disease or not, right? So those kinds of insights, you would never know if you don't try to vet these models and see what's going on with their predictions.
Fascinating. That's super, super cool. Awesome. We have, it looks like I sort of stole the question from the Q&A box, but it says, I think Scott just asked the question, but let me ask the audience version of it. Daniel Alabi asks, to what extent do people ask domain experts like medical professionals to rate the explanations and then incorporate that? You just talked about how it would happen. So now the question is, does it happen yet?
Yeah, great question. So we actually have like a PNAS paper coming out, which exactly tries to deal with this kind of an issue. So where we talk to the medical, so there are two sets of things. So first of all, we did like large scale user studies with medical professionals to understand if adding explanations is going to help them in any way in their job on two metrics. One is the decision making accuracy and the other is the time taken to make a decision, right? So those two metrics, and what we observed is that while explanations, if you give some notion of legitimacy or accuracy of the explanations, if you give that, they can help with improving the accuracy of the decision making of the doctors, while of course it's going to add a little bit to the time it takes for them. But if you give an explanation without showing any kind of metric about how reasonable it is, then doctors are over trusting explanations even when explanations could be wrong. And that is one way of like understanding their behavior and some insights. And also turning to the other side, also we are trying to develop some recent work is trying to develop some systems where doctors can basically set, like there is like a almost like a bar where they can set trade-offs between this much uncertainty, or like this much is how I would like to emphasize on stability, and then you can sort of like it can work through those trade-offs that they're looking for in real time and like give them explanations.
Okay, I think we have time for one more very quickly if you're willing to stick with us. I know we're running a little bit over, but awesome. So last question from M. Krishnan. Do you see AI fairness, bias, and explainability as being interconnected rather?
Yeah, it's a very good question. And the answer to that question is yes. In fact, several of our recent works have been on this topic of attacks on explanation methods, right? So if there is a malignant entity or an adversarial entity that is trying to game your explanation methods, like what would those attacks look like? And all of them, or roughly most of them, are touching the fairness area. For example, one of our recent works is basically about how an adversary can build models in such a way that the model is extremely unfair to any real world data point, but is extremely fair to these off the data manifold points, which are essentially these perturbations. And your methods like these, if you try to use them, people commonly use methods like Lyman Sharp to see if the underlying model is relying on features like race. But we are showing that there can be models designed in such a way that they fool these methods and like stop that from happening, right? But yeah, one of the common reasons why people think of explainability is to also discover underlying biases. But there are also issues with doing that, and that's what some of our recent work is. But I think that is a very, very prominent area of research in the explainability literature.
Awesome. All right. Well, thank you so much. This is totally fascinating and a really, sort of really high energy discussion. Let's, everyone, let's thank Hima. We'll get some applause. Please get some thanks and emotes in the chat. And then we will take a 1-minute break before going on to the last speaker of the show. Thanks again.
Thank you.
So cool.
Thanks, Scott. Thank you, everyone. Bye.
All right. Is that a Blackboard background? I like it.
Yeah, it's a Blackboard.
Love it.
Definitely. A whiteboard background just seems white, right?
That's true. All right, maybe 30 seconds more. Do you want to share your slides? Perfect.
Yeah, sure.
Excellent. Oops. The slides suddenly got really big. There we go.
Now it's okay?
Yeah, better.
Just oh, here we go.
All right. Ready to go?
Yes.
All right. So it is traditional to close out the CMSA Big Data Conference with a rising star, usually one with with recent affiliation to the CMSA, and this year is no different. Recent or current affiliation this year is no different. So our last speaker is Moran Koren, who is holds a PhD in game theory from Technion, and was a postdoc first at the Management Science and Engineering Department at Stanford, where he was supported by a Fulbright scholarship, but then came to the CMSA to be a postdoc. And I'll say a little bit more about this in a moment, but in my research group. So I'm particularly excited, sort of to be introducing him. And he just returned to Israel on a Yitzhak Shamir scholarship for returning scientists. He's also a recipient of the Kaiden Prize, and I'm sure I'm mispronouncing that, but it's very cool. Yeah, so he's been hanging out in my research group for the last year, and I have the unfortunate feature of, because it was pandemic year, I have not actually met him in sort of in the entire duration of the year in person, but we've sort of seen each other like virtually every week, where he's been staying up. I only figured this out like sort of months in, but he's actually been staying up super late because he's been in Israel for much of the period, and so has been like up at 2 in the morning or whatever the heck it is when my research group is meeting. So, sort of the truly extraordinary stamina of a researcher, and also just like an incredible, sort of contributor to the group and scholar. And he is about to tell us about a gatekeeper's conundrum. Let's welcome.
Thank you, Scott.
Moran.
Thank you, Scott. Thank you for having me. It's an honor to be here. So this work is going to be slightly orthogonal to the papers we've just seen. Let me just put it in a context. So when we think about machine learning, we basically think about the following situation, right? We have a bunch of cortex pictures, right? And we want to check a question, for example, whether or not they have a cat or not. So we either give it to humans to characterize, and we divide it into 2 groups. One of them contains the feature we want, which is the cats on the left, and the other is everything that does not contain a cat. And then the logic goes as follows. We're using some sort of algorithm and a law of large numbers. Ability of seeing a cat in a potatoes picture is 0.15. Now, these simple tasks have been very, very useful, so much so that recently there is an explosion of domains in which such methods have been used. And some of these domains, for example, insurance or healthcare, are domains that are affected by human behavior. And once you introduce human behavior, you introduce unpredictability, because humans behave in all sorts of weird ways, and at least to some extent, these machines are not so good at predicting human behavior. Luckily, in the faculty across the street called economics, we have been working the last half a century actually, on questions like this, on how to model human behavior and understand the biases of the data. One group of such models is behavioral models, for example, the framing effect, which is something that people's behavior change according to the context. Disposition effect, for example, the ability to, the tendency to hold on to a failing stock, or an action bias. We much rather do something that just keeps stand and wait. The second group of models, and this is the one I'm going to introduce today, is models that are infected by strategic behavior. For example, moral hazard, people who get insurance are, once they decide to buy insurance, they behave, they take on more risks. Agency, the effort an employee invest in work dependent on the contract he's seeing, and self-selection, which we will be discussing today. And now the real difference between these 2 models is the fact that if the behavior models are sort of probabilistic, right? Then if I simply collect more observations, I will be able to circumvent them. But the strategic behavior are actually changes to the core data generating functions. Therefore, no matter how many observations I will collect, once I've changed the parameter, I'm basically, I can't predict it very well. So no law of large numbers is going to help us here. And this is the type of problem that I'm going to introduce today, and hopefully give the audience, as people who are going to implement data, big data machines or machine learning techniques, some key intuitions on what biases to look for in their data. Okay, so I'm going to look at the self-selection behavior in a situation where we have uncertainty, information need to be collected, and there is some sort of costly application processes. To put things in context, let's look at the following running example. We have an applicant who is applying for a position, wants to apply for a position. Now, the applicant can be highly fitting or she can be low fitting for this specific position. She doesn't know it for sure, but she has some sort of intuition, right? She knows her abilities. She sees the description of the position, and she has some sort of certainty level of how fitting she will be. But in order to get this position, she has to take a test. She has to pass the test. Now, this test is not a perfect test, but it's good enough. Let's assume that if she's highly fitting, she will pass the test for sure. And if she's low fitting, there is a positive probability of her passing the test. And this test is a costly test. If you think about application for a position, this cost is basically driving to the interview setting or passing the test, preparing for the test. If you think of a paper that is being submitted to a journal, then this cost could be the time the paper is under review. And if this cost is very high, or if her intuition is very low, her self-confidence is very low, then she will not apply for this test. And basically, we can organize all the possible signals she can get from being very, very insecure to being very, very secure. And for every cost parameter we'll take, there is some sort of type in the middle who is indifferent. He doesn't care if he applies or not, right? For example, let's assume that she assigns exactly 50% chance to passing this test, right? In this case, she cares, she's exactly get the same utility from applying or from not applying, but all the types between the smiley who holds the coffee and the smiley who wears the sunglasses, for all these signals, she will apply for the test, the position, right? Another thing that is usually a common feature of this sort of selection processes is the fact that the cost is not only for the person who is being selected, but also for the person who does the selecting, right? Consider, for example, a software company who wants to hire an engineer. In order to test him, she will need to invest engineering hours, right? People from the engineering team will have to verify her abilities. In order to save these costs, a lot of companies have introduced a feature that I am calling gatekeeper, right? This is the gatekeeper. If in traditional times, this gatekeeper was the HR person that reads through the CVs looking for buzzwords, today, in many cases, this task is being handed over to a machine learning algorithm who goes through the CVs and decides whether or not to give the applicant a chance at applying for the test in order to get the position, right? So intuitively, one would think that this can only improve the efficiency of the whole process, because I have an entity that is noisily informed, right? But has a good prediction ability that is added to the process. But if this was the case, I would probably not be talking to you today. And as we see, in the interaction between the applicant and the gatekeeper, we get some sort of, we get a couple of interesting results on whether or not this gatekeeper in fact helps the system learn or actually obstruct it. Any questions so far? Is the model clear? Good. So
Good
to
so
put
far.
it in, to put it in a little more rigorous terms, we are asking how does a gatekeeper affect the information aggregation of the selection process? The first question we will examine was, does the introduction of a gatekeeper interfere with candidate self-selection? As we will see, the answer is yes. The second question is, how does the gatekeeper affect the selection correctness? Could it be that the additional gatekeeper actually decreases the probability of hiring a highly fitting candidate and not hiring a low fitting candidate? How does the gatekeeper affect the ability to sift the chaff from the wheat? And the last question we ask is, I'm a game theorist, will be, can we do better than a naive gatekeeper who just waves on anyone who thinks he's fitting? And we'll see that the answer is surprisingly yes, sometimes. So without further ado, let's dive into the model. So first, let's talk about the information structure. As I mentioned, in this entire work, I'm assuming that there is some underlying state of nature, which can be H or L, right? The candidate can be highly fitting or low fitting. But this state of nature is unknown to all the members of the system. There is some known probability that the state of the world is high. For example, this can be thought of as, let's say, if the person is a Harvard graduate, then he's most likely to be high than someone who went to a less prestige school. The test is not perfect, so we're going to make the following assumption. We're assuming that if the state of the world is H, if the candidate is highly fitting, then the probability of passing the test is 1, but there is also a positive probability of passing the test even if they are low fitting. And as we'll see, this assumption introduces some noise into the system and have great importance on the results. Now, both the candidate and the gatekeeper have some sort of prior information, which I will describe soon. So they both have some sort of information on the state of nature, which they are the only one who see. So let's start by analyzing. So are we clear so far on information structures? Okay. So let's start by talking about the candidate, right? So if the candidate is hired, we're assuming that she's getting some positive utility. Right? Once she passes, if she applies and passes the test, then in the state of the world H, her utility is 1. But we will assume that she also gains positive utility if she passes the test and the state of the world is low, right? You can think about it as having Google in my CV for a short period is better than not having Google in my CV, right? Again, depending on how short the period is, but this is the assumption we're making. As I said, the test is costly. So taking the test costs some parameter that we assume is gamma, which is somewhere between 1, which is her utility if she's a highly qualified candidate, and var phi and phi alpha, which is the probability of passing the test times her utility if she's a low fitting candidate. And now, what this structure creates, it creates a situation where if the state of the world is H, she wants to work, she gains positive utility. If the state of the world L, she gets negative utility, but this negative utility is still higher than if she applies for the test and doesn't pass it. And therefore, in the 3 possible scenarios, she prefers, if she decides to apply, she prefers to take the test and pass it. The candidate chooses whether or not to apply for the test. If she doesn't apply, we normalize her utility to 0. And she receives some sort of signal whether or not she is fitting for the job. Now, this signal, the best way to think about it is she's getting some sort of, when she reads it, she gets some sort of intuition based on her work work experience and her knowledge on herself and on what she reads in the paper of the position. And she has some sort of posterior belief of, given the fact that I will be accepted to this job, what will be the chances that I'm highly fitting candidate. And we assume that this posterior belief can be either 0 or 1, which means there are signals that having received them, the candidate knows she's not fitting, and there exist signals that when she receives them, she knows that they are existing. Now this part is going to be a little technical. The way we construct the signal space, it's important because this gives me the several nice features. So we're assuming that the set of signals is some sort of measurable set. At each state, there is a measure according to which the signal is drawn. So there are two measures of distribution, F, H, and FL. And the posterior belief, which I mentioned before, is basically the Radonic-Odin derivative with respect to the measure F, the measure that's written there. Now, if I'm assuming that the density F exists everywhere, then this is basically just a regular Bayesian posterior. I'm calling this the candidate's objective quality because this is a measure of how strong the candidate feels about his own applicability. Another assumption we're making is MLRP, which you don't need to read the text here. Basically, what it means is that if I'm looking at all possible signals and I'm ordering them from the most insecure agent candidate to the most secure candidate, I'm basically, I have two possible distributions. The red one if the state of the world is H, the blue one if the state of the world is L. And my assumption is that as I go to the right, the ratio between the distributions, the densities in both graphs, the ratio between the graphs increases. This combined with the structure of 0 and 1 gives me a very simple structure for candidate behavior, which we'll soon see. And now we'll move on to the gatekeeper. Now we'll move on to the gatekeeper. And the gatekeeper is a much simpler being. He gets a utility of 0 if the position is not filled, right? If, for example, he doesn't pass the candidate, give the candidate pass, or if the candidate decides not to apply, or if the candidate doesn't pass the test. Otherwise, if the candidate is highly fitting, he receives a utility of 1, and if the candidate is low fitting, he receives a negative utility of -3. Therefore, the ranking of the possible scenarios from the gatekeeper's perspective is he prefers to hire a highly qualified candidate, he prefers not to hire at all, or he prefers not to, and then the worst possible scenario for him is to hire a low fitting candidate. This introduces some sort of friction between these two agents. As for his information structure, we'll assume that he's a much more simpler being. He receives a binary signal, either L or H. If you want, I'm running some sort of machine learning algorithm, and if the probability that the picture contains a cat or that the candidate is highly fitting is greater than 0.5, then he receives an H signal, otherwise he receives an LO signal. His signal is on average correct, but he's never perfect. Therefore, even if he saw a very strong signal, it will still not be surely the case that the candidate is highly fitting. Now, what the agents know about each other, they know Q, they know the two distribution measures, but they don't know the realized value of this, of the private signals. The gatekeeper can choose whether or not he lets the candidate through, lets the candidate take the test, right? And for this part of the talk, we will assume that the gatekeeper is a naive gatekeeper, right? What do I mean by naive gatekeeper? I mean he lets the candidate take the test only if he receives a high signal, right? So we are clear on the way on the incentives and actions of the gatekeeper and the candidate. So So without, and now what we want to see is we want to see how this structure affects the behavior of the candidate, how it affects the correctness of the resulting decision. So we'll start with the gatekeeper's effect on candidate self-selection, right? I remind you, this is the effect of introduction of a gatekeeper on the candidate's decision whether or not he wants to apply for the position. And the first result we have is that when facing a naive gatekeeper, the average subjective quality of the applicant is a candidate who played the one, who decided to apply, decreases with gatekeeper signal quality, which means that the better the algorithm I have as a gatekeeper, the worse is the average candidate I will see. And this is interesting because this is an indirect effect of the gatekeeper's presence on the average quality of the candidate. Just to run through the proof real fast, we can calculate the candidate's expected utility from choosing action one as follows. His expected utility is the probability that the state of the world is H given mu and his signal, plus the probability that the state of the world is L given his signal Z, times the probability that he will pass the test, minus gamma, which is the cost he pays if he decides to take the test. After rearranging, we get, using simply Bayes' rule, we get the second row here. And if we assume the gatekeeper is honest, then we can just replace the strategy of the gatekeeper with the values Q if the state of the world is J, and 1 minus Q if the state of the world is L. This gives me a very simple structure of when decision rule of when will the applicant decide to apply. He applies only if he gets signals for which this condition is satisfied. The ratio, the likelihood ratio of his posterior is greater than this expression, where the first element here is the ratio between the utility in state H and state L. Here we see the likelihood ratio of the prior belief. And here we see the likelihood ratio of seeing a gatekeeper who sees a low signal divided by a gatekeeper who sees a high signal. And as we see, if we denote the subjective quality for which the candidate is indifferent, if you remember the smiley holding the coffee cup, this is basically this is the lowest possible type that will decide to apply. And as we can easily see, because Q is greater than half, this function decreases in Q, which means that by introducing a gatekeeper, we've introvertibly made the candidate more prone to take risks. If the candidate was indifferent before, and I've increased Q, he will now decide to apply. I'm using the assumption of MLRP and the full support to get a uniqueness of this threshold. And therefore, just by decreasing X, I know for a fact that I've decreased the average subjective quality. Which means, if we remember just to remind, this means that the guy with the coffee cup for higher Qs moves to the left. Now, interestingly enough, if we have a perfect gatekeeper, which means if Q goes to 1, then the guy with the coffee cup will reach 0, which means everybody will simply apply. And if we have half, then he will not reach if the gatekeeper is very, very bad, he will not reach 1 because he still have costs, but he will stop somewhere in the middle, but he will move to the right. So now that we've seen that the gatekeeper have an effect on the behavior of the agents, we're asking, okay, so he has an effect, but if this effect is only a second order effect, if it's the only indirect effect, why should I care? I mean, can there be scenarios in which the gatekeeper actually harms the probability of getting the correct decision? So can this indirect effect dominate? And to do this, we define efficiency, as is commonly done in machine learning. We define efficiency by the probability of choosing correctly, right? So the probability of the agent being accepted times the probability that the state of the world is high, plus the probability of the state of the world is low times the probability of him being rejected if he applies, where psi is the event in which the position is filled. And the way we are denoting, so the way I'm checking this question is I'm comparing the scenario where I have a gatekeeper of quality Q with the scenario where I have no gatekeeper, right? Where the only thing that affects the decision whether or not to take the test, whether or not the test is administered, is the quality of either the private evaluation of the candidate. And I'm denoting this by X hat. Now, theorem 2, which talks about the efficiency, is the first result is that no matter what information structure I have and no matter what prior I have, there exists some quality of gatekeeping such that if the gatekeeper is better than this, correctness improves, right? Not surprising, this means that a good keeper, that a good gatekeeper is good, right? If I have an algorithm that gives me a result that is close to 1, then I'm always gaining from introducing. The second condition says that if this condition, I'm not going to go into it now because I'm talking about it later on, if something happens, then there exists a Q underscore such that whenever Q is lower than this, the introduction of a naive gatekeeper lowers the correctness of the selection process, right? The second part of this theorem says that if the gatekeeper is bad, right, then I don't want to introduce him. Now here comes the surprising part. If this condition is not met, right, then the introduction of a naive gatekeeper of quality Q equals half plus epsilon, right, his quality is very, very close to Q, improves the correctness of the selection process for any arbitrary small epsilon. The third part tells us that even if the gatekeeper is essentially a a coin toss, right? I mean, if Q is very, very close to half, there is no information that is released in the process. But in some cases, I will still want this gatekeeper to exist. It still improves correctness, which the first time I saw it, I thought that this is crazy. I mean, if Q is very, very close to half, there is no informational value for the gatekeeper. Then how come he improves correctness? And the intuition behind it is that if I don't have a gatekeeper, this is the candidate likelihood ratio, right? On the top, I have the probability that the world is high times the probability that the candidate applies if he sees no gatekeeper and if there is no gatekeeper present and the state of the world is exposed high. And below, we get the same level of the same expression for the second state of for a low-fitting candidate, for an exposed low-fitting candidate. So this is a measure of selectivity for the candidate. Now, if this is greater than phi, which phi, remind you, this is the probability of a low-fitting candidate of passing the test. This means that the candidate itself is more selective than the test that is going to be administered, right? I mean, if I knew that everyone in my class studied very, very hard, I wouldn't need a test because I knew that they know the material, right? And the same goes here, right? If I know that I'm only getting the top candidates, then I don't need a test, that I want them to take the test. And as a result, in this specific case, in part 3, correctness improves if you encourage participation, right? So a bad candidate, even a bad algorithm can sometimes be productive. And it's not like a broken clock that is correct twice a day, right? It actually helps the situation. I will not go into the proof of theorem 2. Basically, it's the sketch of the proof is I'm calculating the differences between a scenario where I have gatekeeper and a scenario where I don't have a gatekeeper. And if the gatekeeper is very, very high, I see that no matter what values of parameters I have, this difference is positive. Now, if I'm taking it Q to be very, very low, I need to remind myself that if Q equals half, then I'm basically in the no gatekeeper case from the perspective of the candidate. And there I see that this difference is only greater than 0 if the likelihood of the likelihood ratio of the agent self-selection, the candidate self-selection, is lower than the quality of the test. So far what we've seen is that gatekeeper have an indirect effect. And we've seen that in some cases, this indirect effect actually dominates over the direct effect of the gatekeeper. And we've seen, but in general, we can say that gatekeeping is a good thing. We want to include this algorithm in the way. Now, the question I'm asking, the last question I'm asking for today was, can we do better than this naive gatekeeping, right? Because the logic here is that if I have a honest gatekeeper, a naive gatekeeper, people are less selective. But what if I introduce just a little bit of noise? Thus, I'm correcting for the agent self-selectiveness, right? Because if I'm introducing noise, people will behave more selectively. If they behave more selectively, this might increase the gains from this system. And as I see, so in order to say what is a strategic gatekeeper, let's first define it, right? So a strategic gatekeeper has the same utility as the guy we saw before. The only difference is that now I'm allowing him to play as follows. With probability 1 minus sigma, he will play naively. With probability sigma, he will play 1 no matter what signal he sees, right? So with probability sigma, he will simply let everybody pass. With probability 1 minus sigma, we are basically in the same game as before, right? Now, nobody knows how the gatekeeper will play because this is a mixed equilibrium, and we can think about it as the gatekeeper making some sort of random choice whether or not he wants to wave the candidate through. Now, if in all equilibrium, sigma will be 0, this means that naive gatekeeping is the best. So to look at the gatekeeper's utility function, we can basically have the probabilities the state of the world is high times the probability that the candidate decides to apply and the keeper decides to pass him through given h. Now I remind you that these have two expressions, right? One which is dependent of sigma and one that is not dependent of sigma. Minus d, which is his utility from a low candidate fitting, a low candidate being accepting the position, times the probability of a low candidate passing the test, with the and the probability of the state of the world being low and the candidate applies and goes through the test, which is what is written down here. Now, in order to find an equilibrium, we know that an equilibrium will be a global maximum of this function, right? Now, since we assume that the distributions are continuous and everything is continuous, if I had an exact form of FH and FL, I could have just calculated this equilibrium, right? Now, what's surprising about theorem 3 is that in theorem 3, I know that no matter what information structure, if the prior is sufficiently high, if there exists a mu bar such that for every mu above it, and in every equilibrium, sigma star is greater than 0, right? What does it tell us? It tells us basically that if the prior is very, very high, if the candidate is a Harvard graduate with 10 years experience, it might be to my best interest, to the firm's best interest, to the gatekeeper's best difference, to assign some positive probability that he will simply pass through the test, pass through the gatekeeper and be administered to take the test, regardless of what the condition, what signal did the gatekeeper see. Now, I made a small inaccuracy in what I said. It's not sometimes, it's if the prior is sufficiently high, this will always be the best case. So you can always improve over the efficient gatekeeper. And the proof is extremely simple. Let's assume to the contrary, that the prior is arbitrarily close to 1, and sigma star equals 0 in some equilibrium, right? So I'm assuming that there is, that naive gatekeeping is an equilibrium. By continuity, if sigma equals 0 is an equilibrium, I know that the derivative around 0 will be closer, will be smaller than 0, right? Now, now this is the calculation of the derivative. Now, anyone who is well-versed in Bayesian analysis would say this result is extremely simple, right? It's intuitive, because if mu is sufficiently high, the gatekeeper has a fixed quality. Obviously, in some points, the gatekeeper will much rather give up his own signal and just follow through the public prior, right? Because if the public prior is 1, then this means that the state of the world is definitely a 1, is definitely high, even if the gatekeeper saw a low signal. Now, what makes this result not trivial is the fact that in this model, if the prior is extremely close to 1, this means that the indifferent candidate is really close to 0, right? So it could be very well the case that these two effects balance each other out. So if candidate is very, very successful, if the profile is very, very strong, the candidate might be very, very easily persuaded to apply for this position, right? A Harvard graduate with 10 years experience does not need to worry too much if he's fitting or not fitting Google, and but as I am seeing, Google can still benefit from introducing some noise into the system. And the reason is can be seen in this graph, right? So if we look at the left-hand side, if mu goes very, very close to 1, and I know that these expressions, the distributions go very, very close to 0, then this whole left-hand side goes very, very close to 1 minus q. Now, the left-hand side goes to 0 because if when I calculated this derivative, I see that when mu goes to 1, this derivative goes to 0. So as I approach 1, the behavior of the candidate, the susceptibility of the candidate to the change in strategy also goes to 0. Therefore, and therefore, the system can only gain from introduction of noise. Are there any questions on the results so far? No. Okay, so I will just summarize. My takeaway messages to those of us who are going to construct and implement machine learning algorithms in the field. Gatekeepers are means to reduce selection costs, right? If we have some very costly exam, we want to be able to sift out CVs automatically. But we have to remember that gatekeepers have an indirect effect on candidate self-selection, right? If I know that I will some job has a very costly application process, I will only be allowed to take the test if I'm a highly fitting candidate. Then I will ignore my own private signal and just submit it no matter what. Good gatekeepers are always good. Bad keepers can be good. And gatekeepers are good if the quality of the test is sufficiently high. If the quality of the test is sufficiently high, if my algorithm, if the test is sufficiently good at sifting out bad candidates, then I want to include even a coin toss as a gatekeeper. And finally, in some cases, one can improve the selection process by introducing some noise, which is sort of a closing of the circle to the previous talk and in some way even to Katrina's talk. And this was it.
Awesome. All right. And amazingly, we are perfectly back on time. We've got a few minutes for questions. As a reminder, you can do them in the chat, in the Q&A box, and/or hit the raise hand button. In the meantime, let me ask a quick one. So, do you have a sense of, what would happen if the gatekeeper, like if we had a gatekeeper and some ability to measure the impact on selection? So like, I know that like the number of people who submit papers to my journal goes down, or the number of applicants for the job decreases or something when I introduce the gatekeeper. And I know by how much.
The increase.
Sorry, yes, that's what I'm saying.
Yeah.
Yes, I'm in the reverse comparative static. I know that the number increases, and I know the amount of increase. How much more can we use that?
So in a sense, once the purpose of this point of my modeling technique was to give it as minimum structure as possible, right? But if you assume, for example, that a specific form on the distributions of the gatekeeper of the candidate signals, you can just calculate, right? I mean, you have an algorithm that you know how accurate it is based on previous history, right? Based on the history. And if I assume, for example, let's say that if I assume any form on the candidate's private signal, then I can just calculate and see, calculate exactly what was the change to the.
I see, right. Okay, so if you give yourself that much structure, you basically know precisely what the selection change was.
Yeah.
Is there any like bound in between? Like, is there some intermediate information we could imagine collecting that would make the process even more powerful?
That's a very good question. It's definitely something that I want to. I have no intuition on it because.
Right, you can see it cutting either way, right? You can sort of see this being like best possible for, because there's like maybe might be some like sort of edge distribution, or you might imagine that there's like something else you could use on top of it.
Yeah, it would be crazy, right? Because I mean, the fact that I assume MLRP doesn't mean that I assumed any type of Lipschitzness, right, to the distribution. So if this point is exactly where the density flies up to infinity,
right.
This number can be as big or small as I want it to be.
Cool. All right. We have a question from the chat. From apologies again, I'm probably going to mispronounce your name. Olanrawaju Adegoke asks, what is the level of precision for using gatekeepers to make predictive analysis?
What is the level of precision? 1 second. So as I show in the theorem 2, sometimes it can be half, right? In some cases, if the test is very, very good, the selection process is sufficiently long and tedious or expensive, then even the gatekeeper of precision half can be good, right? I think if I would now implement it in a high-tech company, what I would do is I would just give like an A/B test of noise to sort of get some sort of estimate of this derivative and what happens. But there is no, again, without assuming any functional form, I can think of examples that go either way. That you need to have a very accurate gatekeeper or a very, very noisy gatekeeper.
Got it.
To get the same level of utility.
Okay, super cool. All right, any further questions? Questions going once? Going twice?
I have a question. Yeah. It's another conundrum for you. Sometimes what companies do is that some companies use machine learning algorithms as gatekeepers, but some companies use headhunters as gatekeepers. And I wonder how would you think about the selection between using one method or another? Obviously, the costs are different, but also the quality is different. But is it just as simple as that?
So if I would think, so let's leave this, let's give the question a little more structure. So let's assume that now I have candidates that have a binary signal, right? Both the candidate and the gatekeeper have a binary signal. and the headhunter have a binary signal. Okay. Now, if the headhunter's private signal is stronger than the candidate's private signal, what I want as the system designer is that the headhunter will get this guy no matter what signal this guy had, right? Because let's say that the headhunter's quality is Q and the candidate's quality is Q minus epsilon, right? The best I can do is Q. The signal of the candidate can only introduce nodes. So in this case, I would definitely want to use the headhunter, right? So even if the candidate did not apply, I want to give him an offer, to make him an offer, right? On the other hand, if the candidates have a very strong signal, then I wouldn't want the headhunter to interfere in this process, right? So again, so in this case, you want a good. I think in this case it's more straightforward. You want a good headhunter. A good headhunter is good. A bad headhunter is bad, right? But this is an interesting thing to see to check in the bigger context, the more general model.
And it's also interesting that you thought of costs of tests from the perspective of the candidate, but there is also a perspective of the firm.
No, it's
right?
in the model. It's the minus D part.
Okay, yeah, fair enough.
So yeah, and the reason I'm not analyzing it from correctness perspective is because it's the same. It's very similar, the analysis.
Yeah.
Cool. All right. Any further questions? Going once? Going twice? All right. Let's thank Moran one more time. Let's get some emotes and thanks in the chat and so forth. And then we're actually, this year, because we're all virtual, we're doing a very short, half-day format. So we are actually at the end of the conference. Let me quickly thank those of you who are still here in the audience for being totally awesome and for sticking with us through the entire event. All four speakers once again. Sergey, and he's done a huge amount of sort of organization and sort of coordination. And the other two co-organizers, Xingtong Yao, of course, who's been incredibly generous in hosting this at the CMSA, for now years and years and years, and I've been involved since the beginning, and it's been fantastic. And HT Yao as well, who's also been a co-organizer of this conference since its very first edition. It's a huge honor to have big data at the CMSA, but of course, the most important, sort of people to this whole process are the staff team. So Elena, who's here and has been in the background, like juggling all the logistics and managing everything. We know who the people who really make conferences happen are. Let's thank her and the rest of the CMSA team. Woot. Let's get some more, sort of appropriate emotes in the chat and stuff. And QED. Thank you so much. And we will see you next year, hopefully this time in person. In the meantime, stay safe and, keep studying big data and related fields. QED.
Thank you, everyone.
Oh, and thanks, Jörn. I see you're in the. See you're in the chat with the Q&A. Thanks for coming. He's another CMSA alum.